What if everything you thought you knew about distance and time was merely a limitation of our current perspective? Deep within the equations of general relativity, first penned over a century ago, lies a breathtaking possibility, a hidden doorway woven into the cosmos itself. These are wormholes, theoretical bridges connecting two distant points in space-time, offering a passage that could make a journey across the galaxy as simple as stepping through a portal. We've all stared at the star-dusted tapestry of the night sky, feeling the immense, untouchable void between us and those glittering points of light. But what if that chasm wasn't so vast after all? The very idea challenges our most fundamental experiences of reality, suggesting that the universe is not a vast, empty plane but a dynamic fabric, one that can be folded, twisted, and perhaps even tunneled through. This isn't just science fiction, it's a profound scientific conjecture born from our deepest understanding of gravity and the shape of space-time, a whisper of a cosmic architecture far more incredible than we ever dreamed. The journey into this mind-bending realm begins with a vision of a cosmic shortcut, a tunnel through the universe that could render our current concepts of travel utterly obsolete. Think of the map of the world before we understood the continents. A voyage from Europe to Asia meant an arduous and dangerous trip around the Cape of Good Hope until someone realized you could simply go west. A wormhole presents a similar, yet infinitely more staggering paradigm shift for the cosmos. Instead of spending millennia traveling at the speed of light to reach another galaxy, you could, in theory, step through a gateway and be there almost instantly. This concept touches something deep within the human spirit, our innate desire to explore, to push beyond the horizon, to go further than anyone has gone before. It speaks to a future where the stars are not just destinations for robotic probes, but new shores for humanity itself, all made possible by understanding the hidden tunnels in the fabric of reality. In this video, we are embarking on an expedition to explore 30 of the most incredible theories about these mysterious portals, from the foundational ideas rooted in Einstein's work to the wild, cutting-edge speculations dancing on the edge of quantum gravity and string theory. We will unravel how a wormhole might be formed, how it could theoretically remain stable, and the monumental challenges that stand between this dazzling concept and a practical reality. This is a journey that will stretch your imagination to its absolute limits, confronting you with ideas about parallel universes, time travel, and the very nature of existence. So prepare to have your mind expanded as we dive deep into the science and the speculation, piecing together one of the most thrilling puzzles the universe has ever presented. To truly grasp the wonder of wormholes, we must first travel back in time to the year 1935, to a quiet office where Albert Einstein and his colleague Einstein-Rosen were peering into the deepest implications of his theory of general relativity. They weren't searching for cosmic shortcuts, they were trying to solve a problem. The mathematics describing a simple, non-rotating black hole, what physicists call a Schwarzschild black hole, contained a troublesome singularity, a point where the equations broke down and physics as we know it ceased to function. In their quest to eliminate this mathematical imperfection, Einstein and Rosen made a stunning discovery. Their calculations revealed that the fabric of space-time could be extended, creating a tube-like structure that connected the black hole to another point. This was not just a tunnel through space, it was a bridge to an entirely separate universe, an exit point through a theoretical white hole, a region of space-time where nothing could enter but matter and energy could only pour outward. This elegant solution, born from pure mathematics, was the very first rigorous description of what we now call a wormhole, though they named it an Einstein-Rosen bridge. At its heart, their model presented a profound new geometry for the cosmos. Picture the classic wormhole diagram you've likely seen, a sheet of paper representing our universe, curved into a U shape with a pencil piercing through from one point to another, creating a shortcut. That pencil is the Einstein-Rosen bridge. One end is the black hole, the point of no return, where gravity is so immense that it traps even light. The other end, in their model, was the white hole, a hypothetical mirror image spewing out everything the black hole consumed. It was a beautifully symmetrical idea, suggesting that anything falling into a black hole in our universe might not be crushed into oblivion, but could instead be ejected into a completely different cosmic realm. This was a revolutionary thought, proposing that the universe might not be a single, isolated entity, but perhaps one of many, interconnected by these hidden passageways. Yet, for all its mathematical elegance, this first theory came with a devastating and fundamental flaw. The bridge itself was incredibly unstable. Think of it as a tunnel made of soap film, shimmering into existence for only the briefest moment before instantly pinching off at the middle. The intense gravitational forces within would cause the throat of the wormhole to collapse into a singularity faster than the speed of light, long before any object, let alone a spaceship, could possibly traverse it. Not even a single photon could complete the journey. So, while Einstein and Rosen had uncovered a breathtaking feature woven into the fabric of reality, it was a feature that appeared utterly useless for any kind of practical travel. It was a doorway, yes, but one that slammed shut the very instant it began to open. This initial model presented wormholes less as potential transportation systems and more as fascinating mathematical ghosts, fleeting structures that highlighted the strange and non-intuitive nature of space-time according to general relativity, setting the stage for decades of scientific struggle to find a way to prop this cosmic door open. For decades after Einstein and Rosen, the wormhole remained a beautiful but frustrating mathematical mirage, a cosmic tease hinting at possibilities just out of reach. The central problem was that instant collapse. The universe, it seemed, had built-in safety features to prevent such shortcuts from being used. Then, in the 1980s, a revolutionary question was asked, shifting the entire paradigm. What if we could fix it? This was the challenge taken up by physicists Kip Thorne and his student Mike Morris, who set out to rigorously determine what it would actually take to create a wormhole you could truly travel through, a stable, traversable wormhole. Their work moved the concept from a passive curiosity of geometry into the realm of theoretical engineering, asking not just what wormholes are, but what we could make them be. The key to their solution lies in a truly bizarre form of material, something physicists call exotic matter. Now, this isn't just matter that's strange or alien. It has a specific, almost magical property: negative energy density. To understand why this is so crucial, think of the throat of a wormhole as an archway that is constantly trying to crumble under its own immense weight. Normal matter and energy, with their positive density, only add to this weight, accelerating the collapse, but exotic matter would behave in the exact opposite way. It would possess a kind of gravitational repulsion, actively pushing outward against the tunnel walls to keep them propped open. In the Morris-Thorne wormhole model, this exotic matter isn't just a helpful addition. It's an absolute requirement, lining the entire length of the tunnel's throat to create a stable passageway through which a traveler could theoretically pass unharmed. The geometry of their proposed wormhole is elegantly described by the Morris-Thorne metric, a set of equations that detail its shape and properties. Unlike the fleeting Einstein-Rosen bridge, this is a static, spherically symmetric tunnel. Imagine it not as a dynamic, pinching tube, but as a smooth, hourglass-shaped corridor carved through the higher dimensions of space-time. One of its most remarkable features is that it contains no event horizon, the point of no return that defines a black hole. This means a traveler could enter the wormhole, journey to the midpoint, and if they chose, simply turn around and head back to their starting point. The entire journey could, in theory, be completed without ever encountering the crushing singularities or one-way barriers that make black holes so forbidding. However, the engineering scale required to construct such a thing is almost incomprehensibly vast. The calculations suggest that to stabilize a wormhole with a throat just 1 meter wide, you would need a concentration of exotic matter with a negative energy equivalent to the total positive energy output of the Sun for millions of years. This immediately highlights the monumental gap between theoretical possibility and practical reality. We are not even sure if such exotic matter can exist in the necessary quantities, or if it's merely a mathematical artifact permitted by our equations. Certain quantum effects, like the Casimir effect, demonstrate that negative energy densities can exist in tiny amounts between closely spaced metal plates, but scaling this phenomenon up to a cosmic level is a challenge that may forever lie beyond our capabilities. This single requirement acts as the ultimate barrier, transforming the dream of a traversable wormhole from an engineering problem into a profound question about the fundamental laws of physics themselves. But while stabilizing a wormhole for space travel presents one set of colossal challenges, the implications become even more staggering when we consider their potential for a far more incredible feat: time travel. This brings us to our third theory, which posits that a traversable wormhole could be transformed into a functional time machine. The mechanism relies on one of the most experimentally verified and yet mind-bending consequences of Einstein's special relativity: time dilation. According to this principle, time does not tick at a constant rate for everyone everywhere. For an object moving at a significant fraction of the speed of light, time literally slows down relative to a stationary observer. We know this is true. It's been confirmed with ultra-precise atomic clocks on fast-moving jets and satellites. The clocks on the GPS satellites in orbit, for instance, need constant adjustment for this very effect, or the entire system would drift into inaccuracy. Now apply this to our wormhole. Imagine we have managed to construct a stable Morris-Thorne wormhole with its two mouths sitting peacefully in the same location, synchronized to the same moment in time. They are two doors to the same instant. Next, we take one of these mouths, mouth B, and attach it to a super-advanced spaceship. This ship then embarks on an epic journey, accelerating to near light speed, traveling a great distance and then turning around to return home. For the astronauts on that ship, and for Mouth B itself, time passes more slowly due to their incredible velocity. Let's say the round trip takes 10 years from the perspective of everyone who stayed behind with Mouth A. For the crew on the high-speed ship, however, perhaps only 2 years have passed. The crucial point is that this time difference is now permanently imprinted on the wormhole itself. When the ship returns and Mouth B is parked next to Mouth A once more, they are no longer synchronized. Mouth B is now 8 years in the past relative to Mouth A. This is where the true magic, or perhaps the profound terror of the situation, unfolds. The wormhole is no longer just a bridge through space, it has become a bridge through time. If you were to jump into Mouth A, which exists in the present day, you would not simply emerge from Mouth B in a different location. You would emerge from Mouth B into the past, 8 years earlier from when you jumped in. You have traveled back in time. The entrance is in your present, but the exit is in your past. Even more astonishingly, this time machine is a two-way street. Someone from that past era could, in turn, step into Mouth B and instantly emerge from Mouth A into your future. You have created a stable, traversable tunnel connecting two different points in time. This immediately confronts us with one of the most famous conundrums in all of speculative science, the grandfather paradox. What if you, after stepping out into the past 8 years ago, were to accidentally prevent your own grandfather from meeting your grandmother? This would create a logical inconsistency so severe it seems to violate the very foundation of cause and effect. You would never be born, and therefore could never have traveled back in time to commit the act in the first place. It's a loop of impossibility that makes rational sense seem to break down. Some theoretical resolutions to this paradox have been proposed, such as the idea of parallel timelines, where your actions in the past simply create a new, divergent reality, leaving your original timeline untouched. But the very existence of such a paradox suggests that the universe might have a fundamental aversion to this kind of meddling. This is precisely the intuition that led the legendary physicist Stephen Hawking to propose his chronology protection conjecture. Hawking essentially argued that the laws of physics must contain a built-in mechanism, much like a cosmic security system, that prevents macroscopic time travel to the past. He suggested that whenever conditions arise that could create a closed time-like curve, the technical term for a path through space-time that loops back onto its own past, some physical process would always intervene to stop it. In the case of our wormhole time machine, this could mean that the vacuum fluctuations of quantum fields would build up to infinite energy the moment someone tried to use the wormhole to travel into their own past, effectively destroying the tunnel in a flash of radiation before any paradox could occur. While this remains a conjecture, it represents a compelling argument from one of our greatest scientific minds, that the universe we live in might be constructed in such a way that the past is, by its very nature, protected and untouchable, preserving the consistent and logical flow of time that we all experience. But if the grand cosmic architecture of wormholes feels impossibly large and distant, our next theory shrinks the entire concept down to a scale so small it defies human imagination. We must journey from the vastness of interstellar space to the frenetic, probabilistic depths of the quantum realm, to a concept proposed by the brilliant physicist John Wheeler known as quantum foam. At the enormous scales of planets and galaxies, space-time appears as a smooth, continuous fabric, the serene stage upon which the cosmic drama plays out. However, if we could zoom in to the very smallest possible unit of measurement, the Planck length, a distance so minuscule that a single proton would be as large in comparison as a tree is to our entire solar system, this serene picture completely disintegrates. Here at the foundation of reality, space-time is anything but smooth. It is a seething, turbulent, and chaotic foam. This quantum foam is the ultimate manifestation of Heisenberg's uncertainty principle on the geometry of space-time itself. Just as virtual particle pairs spontaneously blink into and out of existence, borrowing energy from the vacuum for fleeting moments, the very fabric of space and time is subject to violent, random fluctuations. The geometry of this foamy substrate is constantly warping, twisting, and bubbling, and within this incredible, submicroscopic frenzy, our theoretical wormholes make their most fundamental appearance. Tiny tunnels, bridges, and handles in the space-time continuum are constantly forming, breaking, and reforming. They are not structures built by cosmic engineers, but natural, ephemeral features of the vacuum itself, as intrinsic to the fabric of the universe as waves are to the ocean. The sheer scale of these phenomena is almost impossible to internalize. A typical wormhole in the quantum foam would have a diameter on the order of the Planck length, which is about 10 to the power of -35 meters. To say these are microscopic doesn't even begin to cover it. They are over a billion times smaller than a single proton. Their lifetimes are equally fleeting, lasting only for a minuscule fraction of a second before the violent fluctuations of the foam cause them to pinch off and vanish back into the energetic vacuum from which they emerged. For all practical purposes, these are not traversable portals, but rather ghostly flickers in the structure of reality, far too small and unstable for anything, even a single subatomic particle, to pass through. They are the universe's most fundamental and short-lived shortcuts, yet this leads to one of the most speculative and captivating ideas in all of theoretical physics. Could an unimaginably advanced civilization, one that has mastered the manipulation of reality at the quantum level, learn to harvest these natural phenomena? The concept suggests that such a civilization might not need to build a wormhole from scratch, with its insurmountable requirement for exotic matter. Instead, they might develop a technology to somehow detect, capture, and stabilize one of these naturally occurring quantum wormholes at the very moment it pops into existence. The next step would be even more incredible, somehow enlarging it, feeding it energy and exotic matter to force its throat to expand from a width of 10 to the negative 35 meters to a size large enough for a ship or even an entire civilization to pass through. It would be a form of cosmic gardening, nurturing a seed of space-time structure into a fully grown, usable gateway. Visualizing this process is a profound challenge, but it evokes a powerful image. Imagine a network of space-time that, at its most fundamental level, looks less like a smooth sheet and more like a wildly boiling pot of water, with bubbles of every possible geometry constantly forming and popping. An advanced technology would be like a fisherman on this raging quantum sea, casting an impossibly fine net to catch one specific perfect bubble, a nascent wormhole the moment it forms. Then, with unimaginable precision, they would inject it with a form of stabilizing energy, a scaffold of negative energy density, preventing its instantaneous collapse. As this energy flows in, the microscopic tunnel would begin to swell, growing from a subatomic curiosity to a macroscopic marvel, a stable bridge through the higher dimensions. This speculative process transforms a fundamental, if ephemeral, feature of physics into the ultimate tool for cosmic exploration, suggesting that the blueprints for interstellar travel might be woven into the very quantum code of the universe, waiting to be deciphered by an intelligence advanced enough to read them. While the idea of stabilizing a quantum wormhole feels like the ultimate engineering challenge, a radically different perspective emerged in 2013, one that suggests these cosmic tunnels aren't just structures we might build, but are in fact fundamental to the very nature of reality itself. This is the ER equals EPR conjecture, a proposition so profound it aims to unite the two greatest pillars of modern physics, general relativity and quantum mechanics, by linking the geometry of wormholes to the enigmatic phenomenon of quantum entanglement. The ER stands for the Einstein-Rosen bridge, the original wormhole we just discussed, while EPR refers to the Einstein-Podolsky-Rosen paradox, a famous thought experiment from 1935 designed to highlight what Einstein called spooky action at a distance. For decades, these were viewed as completely separate, unrelated ideas, one about the large-scale structure of space and time, the other about the bizarre connections between tiny particles. But physicists Juan Maldacena and Leonard Susskind boldly proposed that they are, in fact, two different descriptions of the very same thing. To grasp this, we first need to understand the spooky action that so troubled Einstein. Quantum entanglement occurs when two particles, say two electrons, are created or interact in such a way that their properties become inextricably linked. Imagine you have a pair of magical gloves. You put one glove in a box and ship it to a friend on the other side of the galaxy while you keep the other. The moment you open your box and see you have a left-handed glove, you instantly know with 100% certainty that your friend has the right-handed one. In the quantum world, it's as if the gloves weren't left or right until the very moment one was observed, and that act of observation simultaneously defined the nature of both gloves, no matter the distance separating them. This instantaneous connection, which has been repeatedly verified in experiments, seems to violate the cosmic speed limit set by the speed of light, and it deeply disturbed Einstein because it suggested information was traveling faster than light. Now here is the breathtaking leap of the ER equals EPR idea. Maldacena and Susskind suggested that this spooky connection isn't some invisible, instantaneous signal flying through space. Instead, they propose that every pair of entangled particles is, in fact, connected by a microscopic wormhole, an Einstein-Rosen bridge, that vast, empty space between you and your friend across the galaxy. According to this view, it's not truly empty for the entangled particles. They are not communicating across a gap. They are linked by a tiny, Planck-length tunnel woven into the fabric of space-time itself. The connection isn't spooky, it's geometric. The reason we can't send a faster-than-light message through this connection is the same reason the original Einstein-Rosen bridge was useless for travel. The wormhole is not traversable. It's an incredibly narrow, non-traversable bridge, but it physically links the two particles, providing a hidden geometric structure that explains their perfect correlation. This conjecture has staggering implications, particularly for solving one of the most vexing problems in theoretical physics, the black hole information paradox. This paradox arises from Stephen Hawking's discovery that black holes slowly evaporate over astronomically long timescales, radiating away their mass until they potentially vanish completely. The problem is that this Hawking radiation appears to be completely random, containing no information about the original star or matter that formed the black hole. This would violate a fundamental principle of quantum mechanics: that information cannot be destroyed. So, where does the information go when the black hole evaporates? The ER equals EPR idea offers an elegant, if mind-bending, solution. It suggests that the pairs of entangled particles that are created during the Hawking radiation process, one particle falling into the black hole and its partner flying away, are connected by these microscopic wormholes. The information isn't lost, it's not even inside the black hole. It is encoded in the vast, complex web of entanglement connections, mediated by these wormholes between the interior of the black hole and the external radiation. The event horizon, in this view, is not a stark, one-way wall, but is subtly connected to the outside universe through a labyrinth of quantum threads that are, at their heart, geometric bridges. This leads to the most profound implication of all, the nature of space-time itself. The ER equals EPR conjecture blurs the line between geometry and information, suggesting that the very fabric of space and time, the stage upon which the universe plays out, may not be a fundamental background. Instead, it might be an emergent property, a kind of illusion that arises from a vast, underlying network of quantum entanglement. Think of a three-dimensional image on a movie screen. The image seems solid and real, but it is actually generated by millions of tiny pixels of light. In this analogy, the smooth, continuous space-time we experience is the three-dimensional image, while the countless entangled particles connected by their microscopic ER bridges are the underlying pixels. The connectivity of space, the fact that one point is next to another, may literally be built from these quantum connections. It's a concept that turns our understanding of reality inside out, proposing that what we perceive as empty volume is actually a dense tapestry of information and geometric links. While this remains a conjecture at the frontier of physics, it provides a powerful, compelling vision for a potential theory of quantum gravity, one where the wormhole is no longer just a cosmic curiosity, but a fundamental building block of the universe. But what if we didn't need to invent exotic matter or manipulate quantum foam? What if the universe, in its violent birth, already forged the raw materials for these cosmic tunnels? This leads us to a theory that trades high-tech engineering for cosmic archaeology, proposing that we might construct wormholes from the universe's most ancient and bizarre relics, cosmic strings. These aren't the strings of string theory. They are something far stranger, hypothetical, one-dimensional defects in the very fabric of space-time, thought to have been frozen into existence during the earliest, most energetic moments after the Big Bang. As the newborn universe expanded and cooled, it underwent a series of profound phase transitions, similar to how water freezes into ice. And just as freezing water can trap air bubbles or form cracks, the rapid cooling and stretching of space-time could have trapped incredibly dense, filamentary structures of pure energy cosmic strings. To even begin to imagine a cosmic string is to push the limits of our comprehension. Picture an entity that is thinner than a single proton, yet so incredibly dense that just a single mile of it could contain more mass than our entire planet. They are true one-dimensional objects having length but essentially no width, and they possess unimaginable tension, trillions upon trillions of times greater than the tensile strength of steel. A cosmic string cutting through space would warp the geometry around it in a unique and dramatic way. Because of their immense density, they act as ultimate gravitational lenses. If one were to pass between you and a distant star, you wouldn't see one image of the star. You would see two identical, perfectly clear images of it, one on either side of the string, a phenomenon known as gravitational lensing that would provide a ghostly signature of its presence. Now, the theory of using these relics for wormhole construction hinges on their interaction. If two such cosmic strings, each carrying its unfathomable tension, were to slide past each other at incredibly high speeds, their combined gravitational influence could warp the local space-time so severely that it pinches off, creating a bridge, a wormhole, connecting two distant regions. The mathematics suggests that the specific geometry required depends on the string's relative velocities and orientations, but the underlying principle is that the energy to create the distortion is provided by the strings themselves, relics from the dawn of time doing the heavy lifting. It's a concept that feels almost mythological, as if we are finding a way to weave the foundational scars of the cosmos into a functional tool. The hunt for these cosmic strings is one of the most exciting frontiers in modern cosmology. Astronomers search for their signatures in multiple ways. The most promising is through their gravitational footprint. A moving cosmic string would create a unique, linear discontinuity in the cosmic microwave background radiation, the afterglow of the Big Bang. It would literally leave a sharp, cold stripe across this ancient light. Furthermore, the violent oscillations or intersections of cosmic strings would be cataclysmic events, rippling space-time itself and producing powerful bursts of gravitational waves that observatories like LIGO and Virgo could potentially detect. Finding a cosmic string would not only confirm a key prediction of early universe cosmology, but would also reveal the existence of objects with the precise properties needed to, in theory, engineer a wormhole. Of course, the challenges are as immense as the strings themselves. First, we have no confirmed observation of a cosmic string, so their existence remains, for now, purely theoretical. Second, even if they do exist, finding two of them and then orchestrating their high-speed interaction is a task of literally cosmic proportions, requiring a level of control over the universe that is almost godlike. There's also the potential for catastrophic side effects. The process of creating a wormhole from colliding strings would likely release an astronomical amount of energy in the form of gravitational radiation, potentially disrupting nearby star systems. Yet, this theory stands as a powerful testament to the ingenuity of theoretical physics, suggesting that the blueprints for the universe's greatest wonders might have been written at the very moment of its creation, waiting in the voids between galaxies for intelligence advanced enough to read them and put them to use. While the wormhole captures our imagination as a cosmic doorway, another equally fascinating concept offers a different kind of shortcut, one built not as a tunnel but as a track. This is the Krasnikov tube, a theoretical model proposed by physicist Sergei Krasnikov in the 1990s that functions less like a portal and more like a supernaturally efficient subway system laid directly through the fabric of space-time. Imagine a scenario where a starship embarks on a one-way mission to a star system 10 light-years away. Even traveling at a significant fraction of the speed of light, the journey there would take decades from the perspective of mission control back on Earth. The Krasnikov tube proposes that this ship could, as it travels, actively modify the space-time behind it, permanently warping the geometry along its path to create a specialized corridor. The mechanics of this are subtle but profound. As the spacecraft moves outward, it would utilize a form of theoretical engineering, perhaps involving hypothetical materials or fields with negative energy density, similar to what stabilizes a wormhole, to alter the local cosmological constants along its route. It wouldn't be moving space itself, as in the Alcubierre warp drive concept, but rather leaving a permanent, stretched region in its wake. Think of it like a cosmic paving machine. As it travels forward, it lays down a permanent road where the rules of distance are fundamentally different from the surrounding space. This newly created region, the tube, possesses a remarkable property. The space within it is effectively compressed for anyone traveling in the opposite direction, back towards the starting point. This leads to the tube's most incredible feature. Once the ship reaches its distant destination and the tube is fully constructed, the return journey becomes trivial. A second ship, or even the original one turning back, could enter the tube and traverse the entire 10 light-year distance almost instantaneously from its own perspective. The arduous decades-long voyage is reduced to a quick trip. This happens because within the tube, the light speed limit hasn't been broken, but the effective distance between the 2 points has been drastically reduced. The tube has created a one-way, pre-shortened path specifically for the return leg of the journey. It's crucial to contrast this with a traditional wormhole. A wormhole is generally conceived as a two-way street, a bridge connecting 2 points that can be crossed in either direction. The Krasnikov tube, however, is an explicitly one-way modification of the universe's geometry. It only benefits travel in the direction back towards the point of origin. You build it on the way out to make the trip home incredibly fast. From the perspective of an external observer watching from outside the tube, nothing appears to be moving faster than light. The second ship making the instantaneous return trip is simply traveling through a region of space that has been permanently altered to have a much shorter internal length. The magic is in the prepared path, not in a violation of physics. Of course, the energy requirements for such a feat are as astronomical as you might imagine. To permanently distort light years of space-time into this new configuration would require harnessing energies on a scale that dwarfs the total output of stars, likely involving the same exotic and poorly understood forms of matter that haunt other faster-than-light proposals. Furthermore, this solution shares a key limitation with the wormhole time machine we discussed earlier. It creates the potential for closed time-like curves and time travel paradoxes if two tubes were to be strategically arranged. Despite these monumental hurdles, the Krasnikov tube stands as a brilliant piece of theoretical work. It demonstrates that the toolkit of general relativity may offer multiple, wildly different solutions for conquering the vastness of space, challenging us to think not just in terms of bridges and portals, but of permanent, sculpted highways etched into the cosmos itself. Now we turn from the solid relics of the early universe to the most dominant and mysterious force shaping our cosmic present, dark energy. This enigmatic component, making up about 68% of the universe's total energy budget, is responsible for the accelerating expansion of the cosmos, a discovery that earned the Nobel Prize in 2011. It acts as a kind of anti-gravity, a pervasive negative pressure that stretches the very fabric of space itself, pushing galaxies apart at an ever-increasing rate. But what if this mysterious force isn't a fundamental field or energy inherent to the vacuum, but is instead a manifestation of something else entirely, the collective effect of an unimaginably vast network of microscopic wormholes? This is a speculative but compelling theory that attempts to solve two profound puzzles with a single, elegant, and deeply weird idea. The connection hinges on a remarkable mathematical similarity. To keep a wormhole's throat from collapsing, as we saw with the Morris-Thorne model, we require exotic matter with negative energy density, a substance that gravitationally repels rather than attracts. Now, look at the description of dark energy in the equations of cosmology. It is also characterized by a powerful negative pressure. In fact, the mathematical form this negative pressure takes in the equations for dark energy is strikingly analogous to the form required for the exotic matter stabilizing a wormhole. This isn't to say that dark energy is exotic matter you could bottle and use, but it suggests that the underlying physics producing the large-scale repulsive effect we see across the cosmos might share a common origin with the microscopic physics that could, in theory, prop open a space-time tunnel. This leads to a grand, almost fractal vision of the universe's structure. We've already discussed the concept of quantum foam, the seething turmoil of virtual wormholes, and other topological fluctuations at the Planck scale. The theory proposes that this foam isn't just a passive feature, it is dynamic and interconnected. Imagine the vacuum of space not as true emptiness, but as an incredibly dense, bubbling sea of ephemeral wormholes, each one a tiny bridge. While individually these wormholes are vanishingly small and short-lived, their collective gravitational influence could be immense. The combined repulsive effect of this ubiquitous, microscopic network could be what we, on the grandest scales of the cosmos, measure and call dark energy. In this view, the cosmological constant, the simplest mathematical representation of dark energy, isn't a fundamental constant of nature but an emergent property, a statistical average of the frantic activity occurring in the quantum gravitational foundations of reality. Visualizing this concept requires a shift in perspective. Picture the familiar cosmic web, that vast, web-like structure of galaxies and dark matter that defines the large-scale universe. Now imagine zooming in past galaxies, past stars, past planets, down to the very fabric of space-time itself. At this ultimate resolution, the serene backdrop against which the cosmos plays out dissolves into a hyperactive, interconnected lattice. Each point in space is not isolated. It is linked to countless other points by these transient, microscopic wormholes. The energy inherent in this ceaseless formation and dissolution of tunnels provides the constant, repulsive push that drives cosmic acceleration. The universe isn't just expanding, it's being gently pushed apart from within by the hidden architecture of its own fundamental fabric. Testing such a grand unification, however, remains one of the most formidable challenges in modern physics. The primary obstacle is scale. The phenomena of dark energy are observable across billions of light-years, influencing the motion of entire galaxy clusters. The proposed wormhole network, however, operates at the Planck scale, a realm 20 orders of magnitude smaller than a proton. Bridging this chasm between the cosmologically vast and the quantum infinitesimal is the holy grail of a theory of quantum gravity which we do not yet possess. Our current instruments cannot probe these minuscule distances, and our cosmological observations can only see the smoothed-out, average effect of whatever is happening down there. Furthermore, our understanding of wormhole physics itself is still largely rooted in classical general relativity, and we don't know how these structures truly behave when full quantum gravitational effects take over. We are, in a sense, trying to decipher the cause of a tide by studying the ocean from space without understanding the nature of water molecules. Despite these immense hurdles, the theory stands as a powerful example of scientific imagination, daring to connect the universe's most mysterious large-scale force with the hidden tunnels that might be woven into the very essence of space and time. Up until now, we've largely considered wormholes as distinct structures, cosmic constructions separate from the terrifying abyss of a black hole. But what if the most common gateway to other realms isn't something we build, but a natural feature of the universe's most enigmatic objects? Not all black holes are the simple, crushing-in points we often imagine. While the Schwarzschild black hole, the static and non-rotating kind, contains a point-like singularity of infinite density from which no escape is possible, the universe has a far more interesting and complex option. Enter the Kerr black hole, named after the mathematician Roy Kerr, who discovered the solution to Einstein's equations in 1963. This is a black hole in motion, spinning at a significant fraction of the speed of light, and its internal structure is a wild, chaotic landscape that completely redefines what a black hole could be. The key difference lies at the very heart of the beast. Instead of a zero-dimensional point where all matter is crushed into oblivion, the Kerr black hole contains a ring singularity. Picture this not as a solid ring you could hold, but as an incredibly thin, circular line of infinite density, rotating so fast that centrifugal forces prevent it from collapsing into a point. It's a loophole in the grim physics of gravitational collapse, a cosmic carousel of pure energy and warped space-time. This ring is not a solid object you could bump into. It's more like a boundary, a tear in the fabric of reality itself. And it's this specific geometry that opens up a universe of staggering possibilities. Crossing the event horizon of a Kerr black hole is just the beginning of the journey. Inside, you would find not an immediate descent into doom, but a region known as the ergosphere, where the very fabric of space is being dragged around by the black hole's immense rotation, a phenomenon called frame dragging. You would be forced to move with this cosmic whirlpool, but you could still, in theory, maneuver. As you plunge deeper, you would eventually encounter the inner horizon, also known as the Cauchy horizon. This is one of the most bizarre and theoretically unstable boundaries in all of physics. While the outer event horizon is the point of no return for the outside universe, the inner horizon is thought to be a place where the predictions of general relativity completely break down. It's here that the energy of all the light and radiation that has ever fallen into the black hole throughout its entire history is thought to pile up, creating a region of potentially infinite energy density. Surviving this theoretical firewall is one of the greatest hurdles, but if you could, you would then be in a position to confront the ring itself, and this is where the magic happens. The equations suggest that the space inside the ring's singularity is not a dead end but a gateway. The ring acts as a portal, an Einstein-Rosen bridge built into the very architecture of a spinning black hole. If you were to pilot your ship through the center of this ring, a feat requiring unimaginable precision to avoid touching the destructive edges of the singularity itself, you would not be annihilated. According to the pure mathematics, you would emerge elsewhere. This could be a different region of our own universe, a shortcut across the galaxy, or, even more incredibly, an entirely separate universe with its own physical laws and history. The Kerr black hole in this interpretation isn't a tomb. It's a turnstile, a natural wormhole formed by the most violent and energetic processes in the cosmos. But the strangeness doesn't stop there. The profoundly warped geometry inside a Kerr black hole also allows for the theoretical existence of closed time-like curves. This is the highly technical term for a path through space-time that loops back onto its own past. Because of the intense frame dragging near the singularity, the distinction between space and time becomes blurred. It might be possible to follow a trajectory that takes you on a journey where you return to the very same event from which you started before you even left. You could, in theory, meet your past self inside the black hole, creating the same grandfather paradoxes we encountered with wormhole time machines. This is not considered a stable or safe feature. Most physicists believe that the buildup of energy at the Cauchy horizon or the influence of quantum effects would destroy such a path before it could be used, acting as a form of cosmic censorship. Yet, the mere fact that the equations of general relativity permit such a possibility within a naturally occurring object tells us that the universe is far stranger than our everyday intuition allows. Visualizing a journey into a Kerr black hole is a breathtaking exercise. Imagine approaching the rotating behemoth, seeing its accretion disk of superheated gas and dust whipping around at relativistic speeds, glowing with intense X-rays and gamma radiation. As you cross the event horizon, the outside universe would not necessarily vanish instantly. The specific geometry could allow you to see it distorted into a bright ring of light ahead of you, while the interior is a chaotic vortex of warped space. Navigating through the inner horizons, you would be surrounded by the ghostly, blue-shifted energy of every star that ever fell into this vortex. And finally, you would see the ring singularity itself a shimmering Chinese letter, 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 a gateway of pure potentiality hovering in the void. Passing through its center would be the ultimate leap into the unknown, a transition from one reality to another, all made possible by the simple, natural act of a star's core collapsing with a spin. So far, we've thought of wormholes as tunnels carved through the three-dimensional space we know. But what if that very space is just a single slice of a much grander, multidimensional reality? This brings us to a theoretical framework where wormholes aren't just possible. They might be inevitable features of the cosmos's true, higher dimensional architecture. The leading candidates for such a framework are string theory and its extension, M-theory, which propose that the fundamental constituents of reality are not point-like particles but incredibly tiny, vibrating strings. For the mathematics of these theories to be consistent, they require more than the three spatial dimensions of length, width, and height that we move through every day. They demand a total of 10 or 11 dimensions, all curled up or hidden from our everyday perception at a scale a billion times smaller than an atom. To make sense of this mind-bending concept, physicists developed the brain model. Imagine our entire universe, every galaxy, star, planet, and you, is not floating in an empty void, but is actually confined to the surface of a three-dimensional membrane or brain, like an image printed on a sheet of paper. This brain is just one of many, all drifting and floating within a much larger, higher dimensional space called the bulk. We are, in a sense, like ants crawling on the surface of that piece of paper, completely unaware of the vast volume above and below us. We can move forward, backward, left, and right, but the concept of moving off the paper into the bulk is as alien to us as flight is to an ant. This is not just a fanciful analogy, it's a serious proposal for why we only experience three spatial dimensions, and it completely reframes the wormhole puzzle. Within this brain world picture, a wormhole can be envisioned in two profoundly different ways. The first is a connection that remains entirely on our brain. Picture that sheet of paper again, but now crumpled or folded in the higher dimensional bulk so that two distant points on its surface are brought very close together. A wormhole would be a tube-like structure that runs along the surface of the paper, creating a shortcut between those 2 points without ever leaving the brain. This is similar to the classic wormhole model we've discussed. However, the second, and even more intriguing, possibility is a tunnel that actually leaves our brain. Imagine a passage that burrows directly off the surface of the paper, diving through the bulk itself, and then re-emerges at a distant point on our brain. This type of wormhole uses the higher dimensional space as a cosmic subway, bypassing the vast distances within our three-dimensional universe entirely by taking a shortcut through a dimension we cannot perceive. This higher dimensional perspective offers a potential solution to the wormhole's greatest obstacle, the need for exotic matter. In the standard Morris-Thorne model within our three-dimensional space, stabilizing the tunnel's throat requires a bizarre substance with negative energy density. But when you view the same system from the vantage point of the higher dimensional bulk, the forces at play change dramatically. The intense gravitational pressure that wants to crush the wormhole shut in our three dimensions could be counteracted or even completely balanced by the gentle curvature of the bulk space itself. The higher dimensional geometry provides a natural scaffolding, a kind of cosmic arch support that holds the tunnel open without requiring any fantastical materials. The exotic matter problem isn't necessarily solved by finding the matter, but by realizing that the stability might come from the gravitational dynamics of the larger, hidden dimensions, making a traversable wormhole a much more natural feature of a multidimensional cosmos. Visualizing this is the ultimate challenge, but powerful analogies can help. Think of our three-dimensional universe as the entire two-dimensional surface of a vast floppy sheet. An ant living on this sheet can only travel across its surface. A journey from one corner to the diagonally opposite corner is a long and arduous trek. Now imagine you as a higher dimensional being can pick up that sheet and fold it, bringing those two distant corners to touch. The ant could now step directly from one corner to the other. This fold exists in the third dimension, a direction the ant cannot comprehend, yet it creates a shortcut within its two-dimensional world. A wormhole in the bulk is like a tiny, thread-like bridge you stitch between those two touching points. The ant crosses the bridge, effectively traveling through a dimension it cannot access, and arrives instantly at its destination. We, in our three-dimensional brain, could be the ants, using a bridge woven through the fourth spatial dimension. The implications of this are staggering. If such bulk wormholes exist, they would not only allow for near-instantaneous travel across our universe, but could also serve as connections to other brains, other parallel universes with potentially different physical laws and particles. A journey through the bulk could take you to a reality where gravity is stronger, the speed of light is different, or where chemistry as we know it is impossible. This transforms the wormhole from a mere transportation device into a gateway to the multiverse, a concept that pushes the very boundaries of scientific speculation. While M-theory remains untested and highly speculative, it provides a mathematically rich and conceptually breathtaking canvas on which the enigmatic wormhole finds a natural and elegant home, suggesting that the ultimate key to unlocking the stars might lie in discovering the hidden dimensions of space itself. But if these cosmic strings and higher dimensional theories feel impossibly remote, our next theory brings the quest for exotic matter right down to Earth, into the quiet hum of quantum laboratories where a proven, tangible phenomenon offers a tiny glimpse of the physics that could one day hold a wormhole open. This is the application of the Casimir effect, a real and measurable quantum force that demonstrates we can, in fact, create regions of negative energy density, the very stuff required to prop open a cosmic tunnel. To understand how this works, we have to revisit one of the strangest tenets of quantum mechanics, the idea that empty space is not truly empty. What we perceive as a perfect vacuum is actually a frenetic sea of activity, where virtual particle-antiparticle pairs constantly wink into and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating and returning it. The Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed with increasing precision over the decades, directly proves this quantum frenzy has real physical consequences. The classic demonstration involves placing two perfectly smooth, uncharged parallel metal plates extremely close together in a vacuum, so close that the gap between them is smaller than the wavelengths of most of the virtual particles flickering around them. Think of the vacuum's energy as a bustling sea of different-sized waves. Outside the plates, all wavelengths of these virtual fluctuations are allowed, creating a kind of background pressure. But inside the narrow gap, only certain wavelengths can fit, much like how only specific sound waves can resonate inside a flute. This restriction means there are fewer virtual particle fluctuations between the plates than there are outside them. This imbalance in quantum activity has a remarkable result, with more virtual particles pushing on the outer surfaces of the plates than on the inner surfaces. The two plates experience a net force pushing them together. They are quite literally squeezed by the nothingness of empty space. The truly crucial part for our wormhole dream, however, is the energy state of that gap. Because the quantum activity inside is suppressed, that region between the plates possesses a lower energy density than the surrounding vacuum. And since energy and mass are equivalent according to Einstein's E=mc², a region of lower than vacuum energy density mathematically qualifies as a form of negative energy density. It's not a large amount, but it's real, it's measurable, and it's the closest we have ever come in a laboratory to creating the exotic matter demanded by the equations of a traversable wormhole. Now scale this idea up from a lab curiosity to a feat of cosmic engineering. The theory suggests that a civilization with godlike control over matter and energy could, in principle, use this effect to stabilize a wormhole. Imagine they have managed to capture or create a microscopic wormhole, perhaps by plucking it from the quantum foam we discussed earlier. The moment it forms, intense gravitational forces want to crush it shut. To prevent this, our advanced engineers would need to line the entire length of the wormhole's throat, the tunnel itself, with a scaffold that constantly exerts an outward repulsive pressure. This is where an array of Casimir devices or something operating on the same physical principle would come into play. They wouldn't be simple metal plates, of course, but perhaps complex field generators or metamaterials designed to create vast, sustained regions of negative energy density, all carefully arranged to counteract the tunnel's natural tendency to collapse. Visualizing this stabilization process is like imagining the most delicate surgery on the fabric of space-time itself. The wormhole, a shimmering, unstable filament, would be threaded through a series of concentric rings, each one generating a powerful Casimir-like field. As these fields activate, they would create a kind of quantum repulsive force tube, a barrier that pushes outward against the gravitational crush. The wormhole's throat, which would otherwise pinch off in a fraction of a second, would instead be held open, its diameter fixed. It would be like using the gentle but persistent pressure of the quantum vacuum itself to act as a permanent brace, a scaffold made from the manipulated void. The energy required to generate such fields on a macroscopic scale is again astronomical, but the principle is grounded in a quantum phenomenon we know to be real. This offers a tantalizing, albeit distant, hope that the exotic matter problem might not be an absolute dead end, but a monumental engineering challenge waiting for a solution. Taking our journey even further back in time, beyond the formation of cosmic strings and into the very first fleeting moments of reality, we encounter a theory that suggests the most ancient wormholes of all weren't built by anyone, but were born alongside the cosmos. These would be primordial wormholes, relics forged in the inconceivable fire of the Big Bang itself. To find their origin, we must venture into the Planck epoch, a period so early that the universe was just 10 to the negative 43 seconds old. At this time, all of existence was compressed into a volume smaller than a single atom, and the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single superforce. In this seething, unimaginably dense state, the very concepts of space and time as we know them break down. The cosmos was a chaotic quantum foam, as we discussed earlier, but on a universal scale. Here, in this roiling frenzy, the first wormholes could have spontaneously bubbled into existence, not as microscopic curiosities, but as quantum gravitational fluctuations woven into the infant fabric of space-time. The crucial mechanism that could have preserved these nascent tunnels is one of the most important ideas in modern cosmology: cosmic inflation. This was a period immediately after the Planck epoch when the universe underwent a faster-than-light exponential expansion, doubling in size trillions of times over in a minuscule fraction of a second. This inflationary burst acted like a cosmic enlarger, a tiny quantum fluctuation in the space-time metric. A tiny wormhole just a Planck length across would have been caught in this incredible stretch. As the fabric of the universe expanded exponentially, this wormhole would have been inflated along with it, its throat stretching from a sub-microscopic width to a potentially macroscopic size. Imagine a tiny bubble in a piece of dough. As the dough is kneaded and stretched to an enormous size, that bubble expands into a large cavity. In the same way, the violent, rapid expansion of the universe could have frozen these wormholes into the large-scale structure of reality, transforming them from fleeting quantum events into permanent, fossilized features of the cosmos. This leads to a fascinating and profound question. If these primordial wormholes were created in such vast numbers during the Big Bang, where are they now? One compelling possibility is that they could be hiding in plain sight, making up part of the universe's most elusive substance, dark matter. For decades, we've known that about 85% of the matter in the universe is invisible, only revealing itself through its gravitational pull on galaxies and light. The identity of this dark matter remains one of physics' greatest mysteries. Primordial wormholes present a unique candidate, Unlike theoretical particles like WIMP or actions, a wormhole is a topological defect in space-time, a structure, not a particle. A network of such relics scattered throughout the universe and interacting only through gravity would perfectly mimic the observed effects of dark matter. They would clump in halos around galaxies, bending the path of light through gravitational lensing, yet remaining completely invisible to telescopes. They could even have acted as gravitational seeds around which the first stars and galaxies coalesced, their subtle gravity providing the initial overdensities that ignited the formation of the cosmic web we see today. How could we ever hope to detect such an ethereal relic? Astronomers have proposed several ingenious methods. The most promising involves their gravitational lensing signature, but with a specific twist. A primordial wormhole, unlike a star or a black hole, would have a unique and bizarre gravitational footprint. Because it is a tunnel, light passing close to it would be bent in a way that is subtly different from the lensing caused by a solid object. If a wormhole were to pass between us and a distant star, we might not see a single magnification event. Instead, we could witness a rare phenomenon called double amplification, where the star appears to briefly brighten not once, but twice in quick succession as light rays are lensed through both mouths of the tunnel. Another signature could be imprinted on the oldest light in the universe, the cosmic microwave background. The gravitational influence of a vast network of primordial wormholes in the early universe would have subtly distorted the patterns of hot and cold spots in this afterglow. As our satellites like Planck map the CMB with ever-increasing precision, they are searching for these statistical anomalies, hunting for the ghostly fingerprint of tunnels written on the first light of creation. Visualizing the early universe as a cosmic wormhole factory completely changes our perspective on the architecture of reality. Picture the moment of the Big Bang not as a single point, but as a frothing, energetic sea where the geometry of space-time was as malleable as hot glass. Wormholes of all sizes would be constantly forming and dissolving in this primeval chaos. Then, the trigger of inflation occurs, an immense repulsive force that acts like a cosmic blowtorch, causing the entire universe to swell at an incomprehensible rate. In this storm of expansion, a fortunate few of these wormholes are caught and stretched, their throats widening from quantum dimensions to astronomical scales before the fabric of space-time cools and solidifies into the more stable state we know today. These ancient relics would now be scattered across the cosmos, frozen fossils of a more violent and plastic age, potentially serving as the invisible scaffolding for everything we see. They would be silent, timeless witnesses to the birth of the universe, and if this theory is correct, they have been threading the cosmos with hidden connections since the very first moment of time. This brings us face to face with one of the most profound puzzles of all. If we could travel through a wormhole into the past, what would stop us from unraveling the fabric of history itself? We've all heard of the classic grandfather paradox, a terrifying loop of logic where you go back and prevent your own birth, creating an impossible contradiction. But what if the universe has a built-in rule, a cosmic safeguard that makes such paradoxes physically impossible? This is the core of the Novikov self-consistency principle, a fascinating proposal by Russian physicist Igor Novikov. He argued that the timeline of the universe is not a fragile thread that can be easily severed, but a single, immutable, and self-consistent loop. If time travel to the past is possible, then anything a time traveler does there must have already been a part of history all along. Your journey into the past was always an event that occurred. Your actions there were already factored into the timeline that led to your journey in the first place. To see how this works, let's construct a detailed thought experiment. Suppose a fire destroyed a crucial library in the year 1985, and in 2025 you learn that a wormhole time machine has been discovered. You decide to travel back to 1985 to save the library's priceless archives. According to the Novikov principle, your attempt is doomed from the start. not by a force field or a cosmic policeman, but by the sheer consistency of reality itself. Perhaps in your rush to extinguish the flames, you accidentally knock over a lantern that was precariously placed but hadn't yet fallen. Your action, intended to prevent the fire, becomes its very cause. Or maybe a security guard sees you, a strange figure from the future, and in his shock he drops his cigarette, igniting the very blaze you came to stop. In every possible scenario, your presence and your actions don't change the past, they fulfill it. The event unfolds precisely as it always did, with your time-traveling intervention being the hidden, missing piece that completed the historical record. The timeline protects itself by ensuring that every cause and effect link remains intact, weaving the traveler's actions seamlessly into the web of what has already happened. This principle imposes a kind of logical constraint on reality, suggesting that free will for a time traveler might be a profound illusion. You may feel you are making choices, but any choice you make in the past will inevitably be the one that leads to the future from which you came. It's like an author writing a novel where a character travels back to an earlier chapter. The character cannot change the plot the author has already written. They can only act out their predetermined role in the story. This view presents the entire cosmos as a single, block universe where past, present, and future all exist simultaneously in a fixed four-dimensional structure. From this perspective, a time traveler isn't altering history. They are simply following a world line that curves back on itself, a path that was always there, waiting to be walked. But there is another, equally compelling way the universe might resolve these logical knots, one that emerges from the strange world of quantum mechanics. This is the many worlds interpretation proposed by Hugh Everett in the 1950s. In this view, every quantum event that has multiple possible outcomes causes the entire universe to branch, splitting off into a vast and ever-growing multiverse of parallel realities. Now apply this to our wormhole time machine. When you step through the portal into the past, you aren't arriving in your own history. Instead, the very act of your arrival causes a quantum branching event. You emerge into a new, parallel timeline that is almost identical to your original past, but now diverges from that moment forward. In this new branch, you can save the library. You can even meet your younger grandfather and have a conversation with him. Your actions create a new, independent reality where the consequences of your visit play out without any contradiction to your original timeline. In your home universe, the library still burned down and your history remains untouched. You have simply become a permanent resident of a new branch of reality, one where your future is now unwritten. So, we are left with two radically different visions of cosmic law. On one hand, Novikov offers a universe of elegant, singular consistency, where history is a finished tapestry and time travel is a closed loop of predestination. On the other, the many worlds interpretation presents a universe of infinite branching possibilities, where every choice spawns new realities and time travel is an act of emigration from one world to another. One theory enforces a single, unchangeable story. The other allows for endless new chapters to be written. Both solutions prevent the logical absurdity of the grandfather paradox, but they do so by proposing a fundamentally different architecture for reality itself. One suggests the universe is a perfectly self-referential equation, while the other portrays it as an endlessly exploding tree of potentialities. The existence of a traversable wormhole wouldn't just be a technological marvel. It would be the ultimate experiment, revealing which of these profound and mind-bending principles truly governs the cosmos. But for all these dazzling theories, from cosmic strings to multidimensional brains, there remains a single, monumental barrier preventing us from declaring any of them physically possible: the chasm between our two most successful and stubbornly incompatible descriptions of reality. For a complete theory of wormholes, we require nothing less than a full theory of quantum gravity. a framework that seamlessly unites the cosmic-scale physics of general relativity with the probabilistic subatomic rules of quantum mechanics. Think of it like this: general relativity gives us the stage, the smooth, curved fabric of space-time upon which the universe plays out. Quantum mechanics gives us the actors, the particles and forces that populate that stage. Yet when the actors try to perform on a stage that is itself warped to an extreme, as it is at the heart of a black hole or within the throat of a wormhole, our two rulebooks give completely contradictory instructions. The result is a cacophony where physics as we know it breaks down, and our beautiful theoretical wormholes dissolve into mathematical singularities and infinities. This fundamental conflict is most apparent when we consider the very structure of space-time. General relativity treats it as a continuous, smooth fabric that can be bent and stretched. But quantum mechanics suggests that everything in nature is ultimately quantized, meaning it comes in discrete, indivisible packets. So, is space-time itself smooth, or is it made of something else? One leading candidate for a theory of quantum gravity, known as loop quantum gravity, proposes a radical answer. Space-time is not smooth at all, but is woven from a fabric of tiny, finite loops. Imagine the fabric of your shirt. From a distance it looks perfectly continuous, but up close, you see it's actually made of individual, interwoven threads. Loop quantum gravity suggests space-time is similar, composed of a network of these one-dimensional loops with a granular structure at the incredibly tiny Planck scale. This has a profound implication for wormholes. In the standard picture, the immense gravitational forces inside a wormhole's throat are expected to crush matter into an infinitely dense point, a singularity. But in loop quantum gravity, there is a limit to how much space can be compressed. You cannot squeeze it smaller than the size of one of these fundamental loops. This introduces a powerful repulsive force at ultra-high densities, which could potentially prevent the formation of a singularity altogether, acting as a natural bridge that keeps the wormhole's throat permanently open without any need for exotic matter. Another major contender, string theory, approaches the problem from a completely different angle. In this framework, the fundamental building blocks of the universe are not point particles but incredibly tiny, vibrating strings. The different vibrational patterns of these strings give rise to all the particles and forces we observe. To make the mathematics of string theory consistent, it requires extra spatial dimensions, and it naturally includes higher dimensional objects called branes, as we discussed earlier. Within this rich theoretical landscape, a wormhole is no longer just a solution to Einstein's equations. It is described by a very specific configuration of strings and branes. A traversable wormhole could be envisioned as a dynamic, tubular structure made from these fundamental strings, connecting two distant regions. The stability of the tunnel would be determined by the vibrational state of the strings lining its throat. Certain resonant patterns could, in principle, provide the negative energy or pressure needed to hold it open. This perspective transforms the wormhole from a feature of pure geometry into a specific, albeit highly complex, object in a universe built from strings. But perhaps the most profound role for wormholes in any future theory of quantum gravity lies in a concept known as the path integral. Pioneered by physicist Richard Feynman, the path integral is a way of calculating quantum probabilities by summing over every single possible history that a particle, or even the entire universe, could take to get from one state to another. In the context of gravity, this means the quantum description of space-time must include a sum over all possible geometries, and this is where wormholes become absolutely inescapable. You cannot just sum over smooth, simple shapes. You must also include every possible crazy, convoluted, and topologically complex shape, and that includes universes connected by wormholes, both within themselves and to other universes. These are often called baby universes budding off from the main one. Including these wormhole geometries in the cosmic path integral has a staggering consequence that shook the world of theoretical physics in the 1980s. It can seemingly alter the values of nature's fundamental constants. Think about a number like the cosmological constant, which governs the expansion of the universe. In our world, it has a very small positive value. But why is it so small? The path integral approach suggests that when we calculate the probability for our universe to have its particular set of constants, we are not just averaging over one history, but over a vast ensemble of histories connected by a labyrinth of wormholes. The result is that the values we measure for fundamental constants might not be fundamental at all. They could be merely effective, average values that emerge from this cosmic froth of interconnected geometries. The wormhole, therefore, is not just a potential transportation device. It becomes a fundamental ingredient in explaining the very laws of physics as we experience them, suggesting that the seemingly fixed rules of our universe are, in fact, the outcome of a gargantuan quantum average over an infinite multiverse of possibilities. But for all this talk of cosmic gateways and fixed portals, what if we could build a starship that carries its own wormhole with it? This brings us to a concept that pushes theoretical engineering to its absolute limit. The wormhole starship, a vessel that doesn't travel across space, but manipulates the very fabric of space-time to bring its destination to it. Imagine you are not sailing across a vast ocean, but instead you are pulling the shoreline towards you, compressing the miles of water in between into a single, manageable step. This is the essence of the idea, and it draws inspiration from a related concept, the Alcubierre warp drive, but takes it to an even more profound extreme. Instead of simply warping space into a wave that the ship surfs, as in the Alcubierre model, this ship would create, stabilize, and navigate its own personal wormhole. The journey would begin not with a roar of engines, but with the silent, terrifying activation of a physics-defying apparatus on board the vessel. This technology would, in theory, generate two distinct mouths of a wormhole directly in front of it. One mouth, the entrance, would remain anchored to the ship, essentially swallowing it whole. The other mouth, the exit, would be projected forward, not by moving through the space in between, but by manipulating the space-time metric itself, effectively placing the exit point at the desired destination light years away. The starship would then be sitting stationary within the protected bubble of the wormhole's throat, a calm eye in the middle of a cosmic hurricane. From the crew's perspective, they aren't moving at all. The entire universe outside the wormhole's walls is what appears to be in motion, streaming past in a brilliant, swirling vortex of distorted starlight and warped space. Inside this bubble, they would be completely shielded from the lethal tidal forces and time dilation effects that would otherwise tear apart any object moving at relativistic speeds, making faster than light travel not only possible but also a smooth and placid experience. The engineering behind such a feat is, to put it mildly, mind-boggling. First, you face the same monumental challenge we've discussed before, creating and stabilizing the wormhole itself. The ship would need to carry or somehow generate an astronomical quantity of exotic matter with negative energy density, using it to line the entire length of the tunnel it is creating in real time, preventing the throat from collapsing the moment it forms. But then comes an even more complex problem: navigation. How do you move the exit mouth? The theory suggests that the ship wouldn't push the exit through space. Instead, it would manipulate the space-time coordinates around the exit mouth, effectively redefining its location relative to the rest of the universe. This requires a level of control over gravity and geometry that is pure science fiction with our current understanding. You would need to precisely aim the exit, calculating not just the spatial coordinates but also the temporal ones, ensuring you don't accidentally emerge a million years in the past or future. This single-ship approach, while epic, leads to a more efficient and perhaps more plausible vision for a future interstellar civilization: the galactic subway system. Instead of every vessel generating its own wormhole from scratch, an unimaginably advanced society could construct a network of pre-established, permanently stabilized wormholes. These would be the ultimate infrastructure project, with gateways anchored in stable orbits around stars, acting as fixed stations. Your starship would then simply travel from your home planet to the local wormhole station, a journey that might still take months or years using conventional propulsion. But once you enter the gateway, you will be instantly transported across thousands of light years to another station in a distant star system. This transforms the galaxy from an impossibly vast expanse into a connected community, where the longest part of any journey is the local commute to and from the portals. The wormholes themselves become the immutable highways, and the ships become the local traffic. Visualizing the moment of transit for such a wormhole starship is a spectacle worthy of the most epic science fiction. Picture the vessel, a sleek construct of a civilization that has mastered physics itself, hovering in the void. At its command, space ahead of it doesn't just warp, it tears. A brilliant, shimmering ring of energy blossoms into existence, its circumference filled with a chaotic, swirling vortex of every color imaginable, a visual representation of the twisted space-time within. The ship moves forward, crossing the event horizon of this manufactured gateway, and is enveloped by the light. Inside the tunnel, the crew sees not darkness, but a maddening corridor of stretched and compressed starlight, a tunnel of cosmic rainbows where the laws of perspective are broken. The journey is instantaneous. One moment, they are looking at the starfield of their origin. The next, the vortex dissipates to reveal an entirely new constellation, a new sun, a new world, all reached not by traversing the gulf, but by bending the map of reality itself to their will. Delving deeper into the quantum enigmas at the edge of a black hole, we confront one of the most heated debates in modern physics, a puzzle that threatens to overturn our fundamental understanding of reality, and where wormholes might provide the key to a solution. This is the black hole information paradox, and it begins with a seemingly simple question with devastating implications. When something falls into a black hole, what ultimately happens to the information it contained? Every book, every person, every elementary particle is defined by its quantum information, the specific spin of its electrons, the unique configuration of its atoms. A bedrock principle of quantum mechanics is that this information can never be truly destroyed. It can be scrambled, but it must be preserved. Yet, Stephen Hawking's revolutionary work showed that black holes aren't completely black. They slowly evaporate over astronomical timescales by emitting a faint glow of radiation. The problem is that this Hawking radiation appears to be completely random, a featureless thermal haze that carries no details whatsoever about the original star or the teacup or the encyclopedia that fell in. If the black hole evaporates completely, that unique quantum information seems to have vanished from the universe, violating a core tenet of quantum theory. For decades, physicists were faced with a grim choice. Either our understanding of quantum mechanics is wrong, or our understanding of black holes is profoundly incomplete. This is where the wormhole, particularly through the ER=EPR conjecture, storms into the debate with a breathtakingly elegant resolution. Recall that this idea proposes that every pair of entangled particles is connected by a microscopic, non-traversable wormhole. Now scale this up to the most extreme gravitational environment imaginable. When Hawking radiation is emitted, it doesn't come out as single particles, it emerges in entangled pairs. One particle, the Hawking radiation we see, flies away into the universe. Its entangled partner falls backwards into the black hole. According to ER=EPR, these two particles are not mysteriously linked across a void. They are physically connected by a Planck-scale Einstein-Rosen bridge. This means the information about what fell into the black hole isn't trapped inside the central singularity, waiting to be erased. Instead, it is instantly transferred through this web of microscopic wormholes to the outgoing Hawking radiation. The information never actually enters the black hole in the way we traditionally thought. It is imprinted on the radiation via these hidden geometric connections. The black hole, in this view, is not an information-destroying monster but a cosmic scrambler, and the wormholes provide the channels through which the information is faithfully, if chaotically, preserved and released back into the universe. However, this beautiful solution inadvertently gave birth to a new and equally ferocious paradox, one that places an astronaut at the event horizon in a terrifying predicament. This is the firewall paradox. To understand it, we need to consider the principle of quantum monogamy, which states that a quantum particle can be maximally entangled with only one other particle at a time. Now consider our pair of Hawking particles. The escaped particle must be entangled with its partner that fell in. But for the information to be preserved, the escaped particle must also be entangled with all the Hawking radiation that was emitted earlier, a complex web of correlations needed to encode the information of what fell in. This is a direct violation of monogamy. The particle cannot be fully entangled with two different things at once. To resolve this conflict and save the laws of quantum mechanics, the only escape seems to be a drastic measure. The entanglement between the two original Hawking particles must be violently severed the moment the black hole becomes old enough to have radiated a significant amount of its mass. The severing of such a profound quantum link would release an immense amount of energy, creating a wall of blazing, high-energy particles, a literal firewall right at the event horizon. This incinerates any astronaut attempting to cross, contradicting the foundational principle of general relativity that insists crossing the event horizon should be an uneventful, tidal force-free experience. So we are left with an impossible choice. Either quantum mechanics is wrong and information is lost, or general relativity is wrong and event horizons are deadly firewalls. The potential resolution, once again, points back to the subtle architecture of wormholes. The firewall paradox arises from assuming that the entangled Hawking particles are separate entities connected by spooky action. But if ER equals EPR is correct, they are not separate at all. They are connected by a physical bridge. The wormhole provides the needed connectivity. In this geometric picture, the information doesn't have to be carried by a forbidden double entanglement. Instead, the complex web of entanglement between all the Hawking radiation particles is mirrored by an equally complex network of microscopic wormholes linking them. This intricate geometry can, in theory, maintain the consistency of quantum mechanics without requiring a firewall. The event horizon remains a peaceful place to cross because the information is being transmitted through these hidden tunnels in the geometry, not through paradoxical entanglements in the void. The infalling astronaut simply passes through the horizon, unaware that the information about their constituent particles is already taking a backdoor route out into the universe. This profound connection between wormholes and information preservation leads us to one of the most futuristic and experimentally relevant ideas: wormhole teleportation. This isn't about sending people or ships, but about transmitting the most fundamental data of all quantum information. The phenomenon is a direct parallel to quantum teleportation, a real-life protocol used in labs today. In standard quantum teleportation, you can transmit the exact quantum state of a particle to a distant location without physically sending the particle itself. This requires a pair of entangled particles, one held by the sender and one by the receiver, and the sender must also transmit some classical information. The ER equals EPR conjecture provides a stunning geometric interpretation of this entire process. The act of quantum teleportation, where information seems to jump from one place to another, can be mathematically described as the information traveling through a wormhole that momentarily connects the two entangled particles. The classical information sent by the sender is the key that holds this microscopic wormhole open just long enough for the quantum data to pass through. In this breathtaking view, every successful experiment in quantum teleportation is a laboratory-scale demonstration of information traversing a Planck-length wormhole, a tiny, controlled manipulation of the fabric of space-time itself. It suggests that the universe's method for handling spooky action is to build infinitesimal bridges, and that advanced quantum computing and communication may, in essence, be the practical engineering of a cosmic wormhole network. But what if the exotic matter we've been searching for isn't just a substance with peculiar energy, but something fundamentally more bizarre? This brings us to a hypothetical material that stretches the laws of physics to their absolute breaking point: negative mass. Imagine an object that, when pushed, accelerates toward you instead of away. A substance whose gravitational field doesn't pull other objects in but actively pushes them out. This isn't merely negative energy density, which we've encountered in concepts like the Casimir effect. This is matter with a negative gravitational mass, and it would be the ultimate tool for wormhole engineering. If exotic matter is the special alloy needed to build the archway, then negative mass would be the perfect, ready-made scaffolding, designed by the universe itself to repel the crushing weight of gravity and hold a wormhole's throat permanently agape. To understand why negative mass is so perfectly suited for this task, we need to revisit the core problem of wormhole stability. The throat of a wormhole is under immense gravitational strain, a constant crushing pressure trying to snap it shut like a rubber band. Normal matter, with its positive mass and positive energy, only adds to this inward pressure, making the collapse faster and more violent. But a lining of negative mass would behave in the exact opposite way. According to the principles of general relativity, the gravitational field generated by negative mass would be repulsive. It would push outward against the fabric of space-time itself. This repulsive gravity would act as a perfect counterbalance to the natural inward crush, creating a stable equilibrium where the tunnel could remain open indefinitely. The wormhole structure would be held in a perfect, delicate balance, the relentless pull of the positive mass surrounding the tunnel perfectly matched by the insistent push of the negative mass lining its interior. It would be a self-supporting arch made from the contradiction of gravity itself. The search for such a substance, however, takes us into the realm of the profoundly speculative. Negative mass has never been observed in nature, and most of our established physics assumes that mass, or more correctly, inertial mass, is a positive quantity. Cosmologists have looked for its signature in the large-scale motions of galaxies and in the precise patterns of the cosmic microwave background, but so far, all the evidence points to the gravitational influence of normal positive mass along with the mysterious dark energy. In particle physics, there are no known candidates for a fundamental particle with negative mass. Its existence would require a dramatic extension of our current models, potentially arising from some yet unknown field or a peculiar state of quantum vacuum that inverts the usual relationship between stress and energy. While the mathematics within general relativity can accommodate negative mass as a solution to Einstein's field equations, turning that mathematical possibility into a physical reality is a chasm we have no idea how to cross. If such a substance could somehow be created or discovered, its implications would extend far beyond stabilizing wormholes, venturing into the territory of the truly paradoxical. Consider a simple thought experiment involving a block of negative mass and a block of normal, positive mass. According to Newton's third law, every action has an equal and opposite reaction. If you push the positive mass, it accelerates away from you. If you push the negative mass, what happens? Because its inertial mass is negative, it would accelerate toward the force, not away from it. Now place these two blocks near each other. The positive mass attracts the negative mass with its gravity, pulling it closer, but the negative mass with its repulsive gravity pushes the positive mass away. This creates a bizarre and endless feedback loop. As the positive mass is pushed away, it still pulls the negative mass along with it, which continues to push the positive mass, leading to a perpetual, self-accelerating motion. The two objects would chase each other across the universe in a runaway acceleration, continuously gaining speed without any external energy input, seemingly creating a perpetual motion machine that blatantly defies the conservation of energy and momentum. Envisioning this interaction can be a delightful mental exercise. Picture a sleek, futuristic spacecraft equipped with a block of this miraculous negative mass material. Instead of using rocket fuel, the ship simply positions the negative mass block in front of it. The ship's positive mass is gravitationally repelled by the negative mass, shooting the ship forward. Simultaneously, the negative mass block is attracted to the ship, following it perfectly. The system propels itself endlessly, an engine that requires no fuel, only the paradoxical push and pull of inverted gravity. This runaway motion is precisely why most physicists are deeply skeptical of negative mass's physical possibility. It opens the door to violations of some of the most sacred principles in physics. The universe appears to have a deep-seated preference for positive energy and mass, a preference that may be a fundamental law preventing such logical absurdities from occurring. Applying this to our wormhole construction, the use of negative mass would be the most elegant solution imaginable. The engineering, while still unimaginably advanced, would be conceptually straightforward. Once a nascent wormhole was created, perhaps by manipulating quantum foam or colliding cosmic strings, engineers would simply need to inject or form a lining of negative mass along the entire length of the tunnel's throat. This lining would automatically generate the necessary repulsive gravitational field, acting as a permanent brace. There would be no need for complex field generators or networks of Casimir plates. The negative mass would do all the work naturally, its very existence ensuring the wormhole's stability. The tunnel would become a self-sustaining feature of space-time, a permanent shortcut in the cosmos held open by the immutable repulsion between positive and negative gravity. This vision represents the ultimate fulfillment of the wormhole dream, where the most outlandish hypothetical substance provides the cleanest and most powerful answer to the universe's most formidable gravitational challenges. Up until now, our journey through wormhole geometries has been dominated by spheres, the elegant hourglass shape of the Morris Thorne tunnel, the ring singularity of a Kerr black hole, the spherical mouths floating in space. But the imagination of general relativity is not so limited. What if a wormhole wasn't a rounded portal at all, but something far more stark and geometric? This brings us to a fascinating and often overlooked class of solutions, wormholes with cylindrical symmetry. These are theoretical structures born not from collapsing stars or quantum foam, but from the mind-bending physics of an infinite, rotating cylinder, and they open up a radically different visual and conceptual landscape for what a space-time tunnel could be. The foundation for these bizarre constructs lies in solutions to Einstein's field equations that describe the gravitational field around an infinitely long, spinning cylinder. In the 1930s, physicist W.J. Van Stockham solved these equations for a cylinder made of rigidly rotating dust, a cloud of particles held together only by gravity and their own rotation. The resulting geometry, now known as the Van Stockham dust solution, has a property that makes physicists both intrigued and deeply cautious. It generates closed time-like curves. These are paths through space-time that loop back onto their own past, creating the potential for time travel. The rotation of the cylinder is so extreme that it literally drags the fabric of space-time around with it, a phenomenon known as frame dragging, but amplified to an incredible degree. This twisting of the cosmic fabric becomes so severe that time itself gets bent into a circle near the cylinder. A traveler following a specific path could, in theory, embark on a journey that brings them back to the same event from which they left before they even departed. But how does a spinning cylinder relate to a wormhole? The connection was further refined through another set of solutions called the Lewis vacuum, which describes the gravitational field outside such a rotating cylinder. When physicists analyze these mathematical descriptions, they find that the space-time around the cylinder doesn't just contain time loops, it can be interpreted as containing a tunnel-like structure. Picture not a spherical mouth but a corridor. The cylindrical geometry creates a bridge that connects two different regions of space-time along its length. One could visualize this as two separate universes or two distant parts of our own being connected by this infinite rotating pillar. Traveling around the cylinder in a specific helical path, a spiral, could effectively transport you from one region to another, not by stepping through a circular gate, but by navigating this twisted cosmic corkscrew. Of course, these models come with a monumental and rather obvious caveat. They require the cylinder to be infinitely long. This is the kind of unphysical assumption that signals we are in the realm of pure mathematical exploration rather than a blueprint for a future engineering project. In our finite universe, an infinite object cannot exist. Any real cylinder would have ends, and those ends would drastically alter the geometry, likely destroying the delicate conditions needed for the wormhole or the closed time-like curves to form. Furthermore, the cylinder must rotate at incredible speeds, posing immense material strength challenges even before considering its infinite length. So why do physicists spend time on these seemingly impossible ideas? The value is not in their direct physical realism, but in the profound insights they offer. By studying cylindrical wormholes, we learn that the property of being a space-time bridge is not unique to spherical symmetry. It is a more general feature that can emerge from different kinds of severe gravitational distortions. This expands our toolkit for understanding the full range of geometries that Einstein's theory permits. Exploring these alternative symmetries is like a cartographer discovering that the world can be mapped with entirely different types of projections. We started with the familiar spherical map, the Morris-Thorne model, which is intuitive and aligns with our experience of stars and planets. But cylindrical wormholes show us a Mercator projection of space-time, a different mathematical framing that reveals strange and new properties, like the inherent connection to time loops, which are less obvious in the spherical case. This helps theorists separate the essential features of a wormhole from the incidental ones tied to a specific shape. It tells us that the core idea, a topological handle connecting distant points, is robust and can manifest under a variety of extreme conditions, guiding our search for a truly universal understanding of these cosmic shortcuts. Just when you thought the concept of a wormhole couldn't get any more abstract, we arrive at a theory that challenges the very nature of dimensionality and reality itself. This is the holographic principle, an idea so profound it suggests that our entire three-dimensional universe, with all its stars, planets, and wormholes, might be a magnificent illusion, a holographic projection from a thin, two-dimensional surface at its edge. To grasp how this applies to wormholes, picture a futuristic credit card with a holographic sticker. That shimmering, three-dimensional eagle that seems to float in space isn't actually a solid object. It is encoded entirely on the flat, two-dimensional surface of the sticker. The holographic principle proposes that our universe operates in a similar, albeit vastly more complex, way. The space we live in, the volume we call the universe, is the three-dimensional hologram. And the information that creates this hologram is stored on a distant, two-dimensional boundary that envelops it like the surface of a bubble. This isn't just a philosophical musing. It's a rigorous framework that emerged from the study of black holes and has become a cornerstone of modern theoretical physics, providing a breathtaking new language to describe what a wormhole traversal might truly be. The seeds of this revolutionary idea were planted in the study of black holes. Physicists like Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, a measure of its information content, is not proportional to its volume as you might expect, but to the area of its event horizon. This was a stunning clue. In everyday life, the amount of information something can hold is related to its volume. A bigger hard drive can store more data. But for a black hole, the ultimate information sink, the maximum data it can contain is limited by the surface area of its boundary. This hinted that all the information about everything that ever fell into the black hole, every atom, every person, every book wasn't lost in the three-dimensional volume inside, but was somehow encoded pixel by pixel on the two-dimensional surface of the event horizon. The interior, the bulk of the black hole, was just a projection of that data. The holographic principle boldly applies this same logic to the entire cosmos, suggesting that our reality is a projection from a vast cosmic film located at the farthest edge of the observable universe. Now, let's place a wormhole into this mind-bending holographic universe. Traditionally, we visualize a wormhole as a tunnel through the three-dimensional bulk of space, a physical corridor you could fly through. But in the holographic description, that three-dimensional tunnel is merely the projected image. The real, fundamental description of the wormhole exists on the two-dimensional boundary. The two mouths of the wormhole, which appear to us as distant spheres in space, would correspond to specific, entangled sets of data or quantum circuits on the boundary surface. The tunnel connecting them in the 3D hologram doesn't exist as a tunnel on the boundary. Instead, the connectivity, the property that makes these 2 points a shortcut, is represented by an incredibly complex and specific pattern of quantum entanglement between those two sets of boundary data. The wormhole is the entanglement. This leads to a truly radical reimagining of what it means to travel through a wormhole. If you were to pilot a ship into one mouth and emerge from the other, from our three-dimensional perspective, you've taken a shortcut through the bulk. But from the fundamental two-dimensional boundary perspective, a very different process has occurred. Your ship, and indeed your entire conscious experience, is just a particular configuration of data on the boundary. To travel through the wormhole, that data must be processed. Your information is, in essence, teleported from the quantum circuit representing the entrance mouth to the circuit representing the exit mouth. This wouldn't be a simple copy-paste. It would be a profound quantum computation that transfers your entire informational state, preserving every quantum detail that makes you, across the vast web of entanglement that defines the wormhole on the boundary. You don't physically move through a tunnel, your data is reconfigured, and your three-dimensional projection simply winks out in one location and winks back into existence in another. The implications of this are staggering, offering a potential resolution to the black hole firewall paradox we discussed earlier. If a falling astronaut and the Hawking radiation are quantum entangled, the holographic principle tells us this is because they are connected by a wormhole in the bulk, and that wormhole is the entanglement on the boundary. There is no separate spooky action that needs to be severed, so there is no need for a deadly firewall to appear. The astronaut's information simply flows through the geometric bridge, and the experience of crossing the event horizon remains smooth, all because the fundamental physics is playing out consistently on the two-dimensional surface where reality is truly encoded. This perspective unifies the laws of quantum mechanics and gravity by suggesting that gravity itself, and the space-time it shapes, is an emergent consequence of quantum information and entanglement on the lower dimensional boundary. The wormhole, therefore, ceases to be just a cosmic shortcut and becomes a vital clue, a macroscopic feature that reveals the deepest hidden structure of our holographic universe. But if traversing our own universe through a wormhole seems like the ultimate journey, prepare for a conceptual leap that stretches the very definition of reality. Could these cosmic tunnels serve as conduits not just across our own cosmic neighborhood, but into entirely separate universes, each with its own unique history and laws of physics? This is the staggering proposition that wormholes might be the ultimate gateways to a multiverse. The idea of multiple universes isn't just science fiction. It emerges naturally from several of our most advanced theories, particularly the landscape of string theory. This framework suggests that the way the tiny, fundamental strings of reality vibrate could be arranged in an almost inconceivable number of stable configurations, each one corresponding to a different vacuum state. And each of these vacuum states could have given birth to its own bubble universe, like one soap bubble in a vast, growing foam of realities. In this cosmic landscape, our universe, with its specific constants like the strength of gravity and the mass of an electron, is just one bubble among a potentially infinite number. Imagine approaching the mouth of a wormhole that has been somehow stabilized and tuned, not to a location in our cosmos, but to one of these other bubbles. As you cross the threshold, the very rules of existence could change around you. You might emerge into a universe where the electromagnetic force is 100 times stronger, a realm where complex molecules could never form and chemistry as we know it is impossible. Or you could find yourself in a cosmos where the cosmological constant is so large that space is tearing itself apart at a ferocious rate, where stars and galaxies never had a chance to coalesce. The journey would be more than just travel. It would be a transition into a fundamentally different state of being, a place where the most basic assumptions you hold about cause and effect, matter and energy might no longer apply. The wormhole, in this context, transforms from a mere shortcut into a dimensional key, unlocking doors to realities that were previously only mathematical speculations. This concept provides a breathtaking new perspective on one of the most profound mysteries in science, the fine-tuning of our universe for life. Why do the fundamental constants have the precise, seemingly delicate values that allow for the formation of atoms, stars, planets, and ultimately, conscious observers like us? The multiverse hypothesis, augmented by wormholes, offers a radical answer. Perhaps our universe isn't uniquely fine-tuned at all. Instead, we simply find ourselves in one of the rare bubbles where the numbers work out, a cosmic oasis in a vast desert of inhospitable realities. The existence of wormholes adds a fascinating layer to this idea. What if our universe's stability isn't entirely its own? The equations of quantum gravity suggest that the path integral, the sum over all possible histories for the universe, must include connections to other universes. In this grand calculation, our universe's constants might not be isolated. They could be influenced or even stabilized by its quantum mechanical interactions with other bubbles through a network of wormholes. Our cosmic bubble might be propped up, its delicate balance maintained by its hidden connections to the rest of the multiverse. Visualizing this cosmic architecture is a challenge that demands the most spectacular imagery. Picture an endless, dark expanse, not of empty space but of pure potential. Suspended within it are countless shimmering spheres, each one a self-contained universe with its own unique internal color and texture. Some glow with a fierce, brilliant light, their energy burning out in an instant. Others are dark and cold, their physics never allowing a single star to ignite. A few, like our own, display a beautiful, swirling tapestry of blues, greens, and whites, and connecting these disparate bubbles are the wormhole's elegant, iridescent filaments of warped space-time, threading through the void between universes. They are not random tendrils but structured bridges, perhaps following their own higher dimensional laws. A journey through one would be a transition not just through a tunnel, but across the foundational landscape of reality itself, a voyage from one set of physical laws to another, making the wormhole the ultimate expression of cosmic exploration and the key to understanding our place in a possibly infinite reality. This brings us to a pivotal crossroads in our journey, where the dream of time travel confronts a formidable cosmic safeguard. We've seen how a traversable wormhole could, in theory, be transformed into a time machine by exploiting time dilation. But what if the universe itself has a built-in security system designed to prevent such meddling? This is the essence of Stephen Hawking's brilliant and provocative chronology protection conjecture. Hawking wasn't just skeptical about time travel. He proposed a fundamental principle of physics, arguing that the laws of nature must inherently forbid time travel to the past to protect the logical consistency of cause and effect. He famously quipped that the absence of tourists from the future is perhaps the strongest argument against its possibility, but his conjecture provides a detailed physical mechanism for why this might be the case. It suggests a universe that is actively hostile to paradox, one that would rather tear apart the fabric of space-time than allow a closed time-like curve, the technical term for a path that loops back onto its own past to become a reality. The linchpin of this cosmic defense system lies in the bizarre behavior of the quantum vacuum right at the moment a wormhole is on the verge of becoming a time machine. Imagine the process of creating one. You have your two synchronized wormhole mouths, and you begin to move one on its high-speed journey to create the time differential. As the traveling mouth returns and the two mouths are brought close together, a critical boundary begins to form in the space between them, a chronology horizon. This isn't a physical barrier you can see, but a mathematical point of no return in the causal structure of space-time. It's the line in the cosmic sand where the future of one mouth begins to loop back into the past of the other. It is precisely at this delicate, fleeting instant, just before the time loop is fully established, that the universe strikes back with a vengeance, using the most fundamental tools at its disposal, virtual particles. To understand the mechanism, we need to return to the concept of the quantum vacuum, that seething sea of virtual particle pairs that constantly flicker in and out of existence. Normally, these pairs are created and annihilate so quickly that they violate no conservation laws. However, the formation of a chronology horizon catastrophically disrupts this gentle equilibrium. A virtual particle pair that spontaneously forms just outside this horizon can find itself in an impossible situation. One particle might cross the horizon and embark on a closed time-like curve, looping back in time and returning to the point of its creation before it even left. It could then interact with its own earlier self or with the other particle in a way that creates a self-reinforcing feedback loop. The particle effectively meets its own past, and this interaction isn't just a one-off event. Because the particle is trapped on a time loop, this interaction happens not once but an infinite number of times. Each cycle amplifies the energy, piling up more and more virtual particles in the same region of space. This runaway process is known as vacuum polarization, where the calm vacuum becomes a maelstrom of concentrated energy. The quantum fluctuations don't average out to zero anymore. Instead, they build upon themselves in an unstoppable crescendo. The mathematics describing this phenomenon shows that the energy density of these accumulating virtual particles would skyrocket towards infinity at the chronology horizon. This isn't a gradual heating, it's a sudden, violent instability. The space-time around the wormhole's throat would be subjected to an infinite stress, a conceptual wall of fire far more intense than the proposed black hole firewall. This energy surge would be so catastrophic that it would inevitably destroy the wormhole itself, causing its delicate throat to collapse into a singularity or simply vaporize it in a flash of radiation. The time machine would be annihilated at the very moment of its birth, ensuring that the past remains a protected, untouchable domain. The profound implication of Hawking's conjecture is that it draws a sharp distinction between the existence of a wormhole and its use as a time machine. The laws of physics, in this view, might be perfectly content to allow stable, traversable wormholes to exist as bridges through space. You could theoretically use one to travel from Earth to the Andromeda galaxy almost instantly. But the instant you try to manipulate that same wormhole to create a time loop, you cross a threshold that triggers a self-destructive fail-safe. The universe seems to permit spatial shortcuts but draws an absolute line at temporal ones. This isn't an argument from a lack of imagination. It's a specific prediction about how quantum fields behave in the most extreme gravitational geometries. a prediction that suggests the cosmos is hardwired for consistency, preserving the very arrow of time that gives our reality its structure and meaning. While the chronology protection conjecture remains just that, a conjecture not yet proven as a fundamental law, it stands as a powerful and elegant argument from one of our greatest scientific minds, proposing that the flow of time may be the most carefully guarded resource in the entire universe. We've explored how wormholes might be forged from relics of the Big Bang or held open by hypothetical negative mass. But what if these cosmic shortcuts are being created naturally all across the universe in the most violent events we can observe? Let's turn our attention to the spectacular cosmic collisions that have now become almost routine for our gravitational wave observatories, the merger of two black holes. When these dark behemoths spiral inward and finally slam together, they release more power in a fraction of a second than all the stars in the observable universe combined, shaking the very fabric of space-time with ripples we can detect a billion light-years away. In our standard picture of general relativity, this cataclysm has a simple, brutal endpoint, the formation of a single, more massive black hole. But some physicists are asking a radical question. Could that final, furious moment of union do more than just create a bigger black hole? Could it, under the most extreme conditions, momentarily stitch space-time into a bridge, forging a temporary wormhole between them? To understand how this might be possible, we need to look closely at the dynamics of the merger itself. As two black holes circle each other in their final death spiral, their event horizons, the points of no return are not static spheres. They are dynamic, churning membranes being stretched and twisted by the immense tidal forces. In the last few milliseconds before the collision, these two horizons don't simply bump into each other like billiard balls. Instead, they begin to merge into a single, highly distorted structure, often described as a dumbbell or peanut shape. Within the framework of Einstein's general relativity, this distorted object rapidly settles down into the smooth, calm horizon of the new, larger black hole, a process called ring-down. But what if our equations are only telling part of the story? Some alternative theories of gravity, particularly certain versions of loop quantum gravity, suggest that in this brief, violent transition, the fabric of space-time might be tormented to such a degree that a topological handle forms, a short-lived tunnel connecting the interior regions of the two original black holes. It wouldn't be a stable, traversable wormhole like the Morris-Thorne model, but rather a fleeting gravitational filament, a cosmic thread that exists for mere instants before the final horizon smooths out. This speculative bridge is thought to be a direct consequence of the quantum nature of space-time proposed by these alternative theories. In loop quantum gravity, for instance, space isn't a smooth continuum but a fabric woven from discrete, finite loops. At the tremendous energies and curvatures present during a black hole merger, this granular structure could prevent the formation of a true singularity, a point of infinite density for a fleeting moment. Instead of an immediate and complete collapse, the intense repulsive forces arising from this quantum geometry could create a high-energy bridge, a Planck-scale wormhole that links the two merging objects. Think of it not as a tunnel you could fly through, but as a fundamental reconnection of the space-time fabric itself, a momentary stitching together of two separate points in the gravitational tapestry before the thread snaps and the final black hole forms. So, how could we ever hope to detect such an ephemeral phantom? The key lies in the gravitational waves, the very signals that have allowed us to hear these collisions. When LIGO and Virgo detect a black hole merger, they don't just measure the final event, they capture the entire chirp, the rising frequency and amplitude as the black holes spiral inward, the violent merger signal itself, and then the fading ring down as the new black hole settles into a quiet sphere. According to the standard general relativity picture, this ring-down signal should be very clean, composed of a specific set of damped oscillations called quasi-normal modes, like a bell being struck and then slowly quieting. However, if a transient wormhole were to form during the merger process, it would leave a subtle but distinct fingerprint on this gravitational wave signal. The formation and almost instantaneous collapse of the bridge would introduce extra high-frequency echoes in the ring-down phase. It would be as if you struck that bell, and just as the main tone began to fade, you heard a faint, distinct series of quicker, sharper chimes right after the space-time continuum itself ringing from the sudden creation and destruction of a topological shortcut. The hunt for these gravitational wave echoes is one of the most exciting and contentious frontiers in modern astrophysics. Several research groups have sifted through the public data from LIGO and Virgo, and some have reported tantalizing, low statistics hints of just such a signal following a few of the observed black hole mergers. These potential echoes appear exactly where some wormhole models predict they should, a faint, repeating pattern superimposed on the main ring-down signal. However, the scientific community remains rightly skeptical. The signals are buried deep in the noise, and distinguishing a true echo from a random statistical fluctuation is an enormous challenge. Other groups analyzing the same data with different methods have found no significant evidence. It's a classic scientific detective story playing out in real time, with the prize being nothing less than a revolution in our understanding of gravity. A confirmed detection would not only provide the first evidence for a wormhole, albeit a transient one, but it would also be a direct signature of quantum gravitational effects, a realm of physics that has remained experimentally inaccessible until now. Imagine the profound implications if such an echo were ever confirmed. Every time two black holes collided somewhere in the cosmos, for the briefest moment that physics allows, a gateway would flash into existence. It would mean that the universe is constantly, if briefly, threading itself with these incredible structures in its most energetic crucibles. These wouldn't be the safe, engineered tunnels of science fiction. They would be raw, primordial, and violently unstable phenomena, snapping shut in a flash of gravitational radiation. Yet their mere existence would tell us that the topology of space-time is not fixed. It can be punctured and connected in new ways, and the blueprints for these connections are written into the laws of quantum gravity themselves. The ongoing analysis of gravitational wave data is in effect a direct test of this breathtaking possibility, listening to the echoes of cosmic collisions for the whisper of a bridge that was never meant to last. From the most energetic collisions in the cosmos to the quietest quantum whispers, the recurring presence of wormholes in our theories paints a picture of a universe that might be intricately connected. But this very possibility forces us to confront one of the most haunting questions in all of science, a question first posed casually over lunch in the summer of 1950. If the universe is so vast and so old, where is everybody? This is the Fermi paradox, the stark contradiction between the high probability of alien civilizations and our complete lack of any evidence for them. As we've pieced together the potential physics of wormholes, a compelling and slightly unsettling resolution to this paradox has emerged, one that suggests our picture of interstellar travel and communication might be fundamentally naive. The core of this theory rests on a simple, logical progression. Imagine a civilization just a few thousand years more advanced than our own, one that has unlocked the secrets of quantum gravity and mastered the stabilization of space-time tunnels. For such a society, building massive, slow-moving generation ships to traverse the void between stars would seem as primitive and inefficient as building a wooden raft to cross an ocean today. Why spend centuries journeying through the empty, hazardous space between points A and B when you can simply build a door that connects them directly? If traversable wormholes are physically possible, then any sufficiently advanced species would inevitably use them as their primary mode of transport and communication, constructing a vast, hidden infrastructure, a cosmic subway system, that bypasses the need for visible, slower-than-light vessels entirely. We wouldn't see their ships in the void because they aren't traveling through the void we can observe. they are traveling beneath it through a network of shortcuts woven into the fabric of space-time itself. This idea dovetails perfectly with one of the more optimistic solutions to the Fermi paradox, known as the zoo hypothesis. In this scenario, a galactic community of civilizations exists, all interconnected by this wormhole network. They are aware of us, much like we are aware of a protected nature reserve or a culturally sensitive, uncontacted tribe deep in the Amazon. Our planet, with its budding biodiversity and nascent intelligence, is designated as a wilderness area or a laboratory for natural societal development. The reason we haven't been contacted or haven't seen evidence of their infrastructure is not out of malice, but out of a form of interstellar ethics, a prime directive to borrow from science fiction. They are intentionally leaving us alone, allowing our civilization to develop organically without interference, waiting for the day we mature enough to discover the fundamental physics required to join the galactic conversation on our own terms. Our inability to detect their wormhole network isn't a failure of our technology, but a reflection of our current place on the cosmic ladder. We haven't yet earned the key to the subway station. However, there exists a much darker and more cautionary interpretation. What if the technology required to create and stabilize wormholes is not just advanced but inherently and catastrophically dangerous? The very physics we've explored hints at this possibility. The manipulation of space-time on such a fundamental level could unleash unpredictable side effects. The process might trigger vacuum decay, a theoretical phenomenon where a bubble of true vacuum expands at the speed of light, rewriting the fundamental laws of physics in its wake and erasing everything in its path. Alternatively, the use of wormholes for time travel, even accidentally, could invoke Stephen Hawking's chronology protection mechanism, resulting in a feedback loop of destructive energy that doesn't just destroy the civilization that created it, but potentially sterilizes their entire region of the galaxy. In this bleak view, the great silence we observe is not a sign of a quiet galactic community, but a cosmic graveyard. The Fermi paradox is solved by a simple, grim filter. The moment a civilization becomes advanced enough to master wormhole travel, it inevitably and quickly obliterates itself through the unforgiving physics of its own creation. The silence is the sound of countless civilizations having already reached for this ultimate power and having been silenced by it. This bifurcated view, the hopeful zoo versus the deadly filter, forces us to look at our own scientific pursuits in a new light. Our ongoing research into quantum gravity, negative energy, and the structure of space-time is not merely an academic exercise. It is, in a very real sense, a race toward a technological threshold that could either unlock the universe for us or serve as our final exam, a test we might only get one chance to pass. The continued silence from the cosmos could be interpreted as a warning sign, suggesting that the technologies we are striving toward are not the gateway to a star-faring future, but a recurring and terminal trap for intelligent life. Every time we peer deeper into the equations of general relativity and quantum mechanics, we are potentially handling the blueprints for our own transcendence or our ultimate destruction, a profound responsibility that lends a new weight to the age-old question of whether we are truly alone. But to venture even further into the unknown, we must confront the most enigmatic frontier of all, not just the fabric of space-time, but the nature of the observer woven into that fabric. This brings us to a theory that sits at the speculative edge of physics and philosophy, exploring a potential and deeply controversial link between wormholes and consciousness itself. We've already seen how the ER equals EPR conjecture ties the spooky connection of quantum entanglement to the physical geometry of microscopic wormholes, suggesting that the universe's connectivity is fundamentally geometric. This introduces a profound concept known as quantum non-locality, where particles can be instantaneously correlated across vast distances without any signal passing between them through conventional space. Intriguingly, some philosophers and a handful of physicists have pointed out a curious parallel. Certain aspects of conscious awareness also seem to exhibit a kind of non-locality. Our thoughts and experiences form a unified, integrated whole that doesn't appear to be neatly located in any single neuron or specific region of the brain. The hard problem of consciousness, why and how physical processes in the brain give rise to subjective experience, remains one of science's greatest mysteries, and this has led to speculative proposals that its solution might require new physics, perhaps even physics that connects to the non-local geometry we see in wormholes. The most radical expression of this idea suggests that consciousness might not be a mere byproduct of the brain, but a fundamental property of the universe akin to space and time. In this view, often associated with philosophies like panpsychism, consciousness is ubiquitous, a basic feature of reality. The intricate network of entanglement that, according to ER equals EPR, forms the very substrate of space-time through countless microscopic wormholes, could also be the ground from which consciousness emerges. The integrated information within a complex system, whether a human brain or a vast quantum network, might be what gives rise to subjective experience. From this perspective, the act of observation in quantum mechanics, where a particle's wave function appears to collapse from a cloud of probabilities into a definite state, isn't just a passive recording. It could be an active process where conscious awareness interacts with the underlying geometric structure of reality, potentially influencing the stability or formation of those microscopic space-time bridges. This leads to the truly mind-bending proposal that a conscious observer could, in theory, influence the stability of a wormhole. We know that to keep a wormhole's throat from collapsing, it requires a violation of the classical energy conditions, something provided by exotic matter with its negative energy density. But what if consciousness, through the probabilistic, non-local nature of quantum mechanics, could somehow coax the vacuum into providing that necessary stabilization? The idea is that a focused conscious intention might act as a kind of catalyst, influencing the quantum fluctuations in the wormhole's throat in a way that encourages the emergence of the negative energy densities needed to prop it open. It would be less about brute force and more about resonance, a subtle alignment of mind with the quantum gravitational foundation of space-time itself. Think of it not as lifting a heavy weight, but as finding the perfect frequency to shatter a glass. The conscious observer finds the precise quantum note that allows the wormhole to stabilize. Of course, it is absolutely vital to approach this concept with a heavy dose of scientific skepticism. This idea resides firmly in the domain of speculation and is far, far removed from the testable, predictive framework of mainstream physics. There is not a single shred of experimental evidence that consciousness can directly influence macroscopic physical systems in this way, and the mechanisms proposed are entirely hypothetical. The overwhelming consensus in neuroscience is that consciousness is an emergent property of the complex computational processes of the brain, not a fundamental force that can manipulate geometry. Critics rightly argue that introducing consciousness as a causal agent in physics often leads to vague, untestable hypotheses that can't be falsified, potentially halting the search for more conventional physical explanations. The history of science is littered with attempts to link mind and matter in ways that ultimately proved to be dead ends. Yet, exploring this controversial intersection forces us to confront deep, foundational questions about the relationship between information, the observer, and reality. The wormhole, in this light, becomes more than a cosmic shortcut. It becomes a symbol for the ultimate interconnectedness of all things. If the ER equals EPR idea is correct, then the fabric of space is literally woven from quantum connections, an immense web of information. And if consciousness is, in some way, a manifestation of integrated information, then our own minds are not isolated islands but intrinsic expressions of that same cosmic network. We are not just looking at the universe from the outside. We are localized knots of consciousness within a universal mind, or at the very least within a universe whose fundamental structure is informational and geometric at its core. This doesn't prove the theory, but it offers a breathtakingly coherent, if unproven, vision of reality. One where the journey through a wormhole and the journey of conscious thought are both explorations of the same deep, non-local tapestry of existence. But what if the monumental challenge of exotic matter isn't a dead end, but rather a sign that we've been looking at the problem with the wrong set of rules? For over a century, Einstein's theory of general relativity has been our unparalleled guide to understanding gravity and the cosmos, but it is not necessarily the final word. This brings us to a fascinating frontier known as modified gravity, and specifically to a family of theories called F of R gravity, where the quest for a traversable wormhole takes a dramatic and promising turn. In these frameworks, the need for bizarre, universe-defying substances might be completely sidestepped, not by finding new materials, but by realizing that gravity itself, when described by a more complete theory, naturally provides the repulsive force needed to prop open a cosmic doorway. To grasp how this is possible, we need to understand what F of R gravity actually changes. Einstein's original equations are derived from something called the Einstein-Hilbert action, a mathematical prescription where the core ingredient is R, which stands for the Ricci scalar, a single number that describes the curvature of space-time at any given point. In standard general relativity, this action is beautifully simple, leading directly to the equations we know. F of R gravity boldly asks, what if this prescription is just the first, simplest term in a much more complex series? The F stands for function, meaning that the action is now based on a function of R, which could include terms like R squared, R cubed, or other more complex combinations. This is not a random tweak. It's motivated by attempts to solve some of the biggest puzzles in cosmology, such as the mystery of dark energy and the peculiar dynamics of galaxies that led to the invention of dark matter. By adding these extra terms, the theory suggests that gravity behaves differently at extremely large cosmic scales or in incredibly strong fields than Einstein predicted. This modification has a profound effect on the architecture of a wormhole. In the standard Morris-Thorne model, the equations of general relativity clearly show that the throat of the wormhole will collapse unless it is lined with a material that possesses negative energy density exotic matter. This is a direct, inescapable requirement of Einstein's formulation. However, when you derive the wormhole solutions using the equations of F of R gravity, something remarkable happens. Those extra terms in the function, the R squared or other components, begin to act like an effective, built-in source of negative pressure. They introduce a kind of geometric tension or repulsive gravity that originates purely from the modified dynamics of the space-time fabric itself. In certain specific models, this repulsive effect can be perfectly tuned to counterbalance the gravitational crush that wants to snap the wormhole shut. The tunnel is no longer held open by a phantom-like substance we have to find and assemble. It is held open by the very shape of the gravitational law, a natural consequence of the universe operating under a slightly different set of rules. This makes the existence of stable, traversable wormholes seem far more natural within these theoretical frameworks. Instead of being bizarre anomalies that require us to hunt for impossible materials, they become expected, even mundane, solutions to the equations of gravity. The wormhole transitions from being a cosmic engineering project to a potential feature of the landscape, much like black holes or stars. The energy conditions that must be violated to prevent collapse are no longer violated by a hypothetical material, but by the gravitational field equations themselves. Theoretically, you could construct such a wormhole using only ordinary matter, the same protons, neutrons, and electrons that make up our everyday world, because the modified gravity does all the heavy lifting. The repulsion comes from the geometry, not from the matter content. This doesn't make building one easy, but it removes what many physicists saw as the most fundamental and potentially insurmountable obstacle. One of the most compelling aspects of F of R gravity is that it isn't just a mathematical fantasy designed to make wormholes work. It's a testable framework that makes distinct predictions about the universe we can observe. For instance, these theories often propose an explanation for the accelerated expansion of the universe that doesn't rely on a cosmological constant or dark energy. The extra terms in the function of R can generate a long-range repulsive force that drives galaxies apart. This means we can look at the large-scale structure of the cosmos, the distribution of galaxy clusters, and the precise patterns in the cosmic microwave background, and check if they align better with the predictions of F of R gravity or with standard general relativity plus dark energy. Furthermore, on the scale of individual galaxies, modified gravity aims to explain the flat rotation curves of galaxies without the need for dark matter. The altered gravitational law would cause stars at the outskirts of a galaxy to orbit faster than Einstein's theory predicts, matching observations without invoking vast halos of invisible matter. Missions like the Euclid Space Telescope and ongoing ground-based surveys are actively gathering data that can constrain these models, potentially ruling out entire classes of them, or, if we're lucky, finding a smoking gun that points toward a modification of Einstein's magnificent theory. This creates a thrilling synergy between the cosmic and the cosmic. The same data we use to understand the fate of the entire universe and the nature of its most mysterious components could also tell us whether the fundamental laws of physics permit the existence of natural wormholes. If future observations consistently favor a specific F of R model that also allows for traversable wormholes, the implication would be staggering. It would suggest that the universe is not only threaded with hidden tunnels, but that their existence is a direct and testable consequence of the same gravitational phenomena we see shaping galaxies and driving cosmic expansion. The dream of a wormhole would shift from a question of engineering to a question of empirical science, waiting for us to decode the correct function of R that describes our reality. We would be one step closer to understanding not just how to build a gateway, but why the universe might have already built them for us. We've traced wormholes through the mathematics of general relativity and into the quantum foam, but now we must confront a feature of the cosmos that governs everything from the steam rising from your coffee to the ultimate fate of the universe, entropy. This concept, often described as a measure of disorder, is central to the second law of thermodynamics, which states that the total entropy of an isolated system always increases over time. Now apply this to a wormhole, a tunnel through space-time itself. Does this cosmic shortcut have its own entropy? Does it contribute to the universe's disorder, or perhaps somehow sidestep it? To explore this, we need to travel back to one of the most profound insights of 20th century physics, black hole thermodynamics. In the 1970s, Jacob Bekenstein made a startling proposition. He argued that a black hole must possess entropy, and that this entropy is proportional to the area of its event horizon, not its volume. This was a radical departure from all intuition. In everyday systems, the entropy of a gas, for example, is related to the volume it occupies and the number of ways its molecules can be arranged. But for a black hole, the ultimate sink of information, the maximum entropy it can contain is written on its boundary. Stephen Hawking later cemented this idea by showing that black holes have a temperature and radiate, meaning they obey the known laws of thermodynamics. The Bekenstein-Hawking formula states that the entropy of a black hole is equal to the area of its event horizon divided by 4 in Planck units. It's a beautifully simple yet deeply mysterious equation that ties the gravitational, the thermodynamic, and the informational into one package. Now let's bring this back to our wormhole. A classic, non-traversable Einstein-Rosen bridge has a throat, a narrow, pinchable neck connecting two regions. If we were to crudely apply the black hole logic, we might guess that this throat area could also be associated with an entropy. After all, it's a defined surface in space-time where dramatic gravitational physics occurs. But here we hit our first major conceptual wall. A traversable wormhole, like the Morris-Thorne model, has no event horizon. An event horizon is a one-way membrane, a point of no return, and it's that very feature which gives the black hole its thermodynamic character. A traversable wormhole, by design, allows things to pass through and even come back. There is no point of no return, so what would its entropy even mean? If entropy is tied to information hidden behind a horizon, and there is no horizon, then does the wormhole have zero entropy? That seems too simple and likely wrong. Perhaps the entropy is instead associated with the complexity of the fields, the exotic matter or the intricate geometry that is required to keep the throat propped open. The very act of stabilizing the wormhole against collapse might require a specific and perhaps enormous arrangement of energy and information, which could be quantified as an entropy. The system is highly ordered, and maintaining that order against the relentless pull of gravity could mean it has a very low entropy, which would be fascinating because throwing anything into it would then increase its disorder. This leads to a wonderfully tricky thought experiment. Imagine you have a stable, traversable wormhole connecting your laboratory on Earth to a spaceship orbiting a star in the Andromeda galaxy. The two mouths are synchronized. Now you take a single particle, a simple hydrogen atom, and you throw it into the Earth-side mouth. From your perspective, the particle vanishes. Almost instantly, it flies out of the mouth in Andromeda. Let's track the entropy. From the perspective of your lab on Earth, you've lost a particle. The local entropy in your lab has arguably decreased slightly because you now have one fewer particle contributing to the disorder of your environment. But in Andromeda, the spaceship now has an extra particle, increasing the entropy there. If we consider the total universe, the entropy has simply been relocated, it hasn't decreased. But what about the wormhole itself? Did its internal state change when the particle passed through? If the wormhole has no entropy, then it acted as a perfect, frictionless pipeline, moving disorder from one location to another without any loss or gain. However, if the transit of the particle somehow excited the fields lining the throat, if it created a kind of thermal echo or vibration within the exotic matter, then the wormhole itself might have absorbed a tiny amount of energy, increasing its own internal entropy. The act of transmission wouldn't be perfectly efficient, and the wormhole would heat up ever so slightly, just like an electrical cable warms up when current flows through it. Now let's make the experiment more extreme. Instead of one particle, imagine you throw a hot, disordered gas, a cloud of high-entropy plasma, into the wormhole. The plasma emerges in Andromeda, and its entropy is now there. But has the overall entropy of the cosmos increased? According to the second law, it must have somewhere in the process. Perhaps the very existence of the wormhole, by providing a new, rapid channel for energy and information to disperse, actually accelerates the rate at which the universe reaches thermodynamic equilibrium. It would be like poking a hole in a barrier separating two chambers of gas. The gases mix, and the entropy increases faster than if they had to diffuse slowly through the barrier. In this view, a network of wormholes would make the universe a much more efficient blender, stirring up matter and energy and driving the cosmos toward its final, uniform heat death more quickly. But there is another, more mind-bending possibility rooted in quantum information. Recall the ER equals EPR idea, where entangled particles are connected by microscopic wormholes. Entanglement entropy is a well-defined concept in quantum mechanics. It measures the entropy of one part of an entangled system when you ignore the other part. In this holographic and geometric view, the entropy of a wormhole's mouth could be directly related to the degree of quantum entanglement between its two ends. The more entangled the two regions are, the larger the wormhole throat and the higher its entropy. This creates a stunning picture. Throwing a particle into the wormhole isn't just moving a physical object, it's altering the pattern of entanglement between 2 points in space. This act could increase the entanglement entropy, which would be a fundamental entropy tied to the connectivity of space-time itself. The wormhole isn't just a tunnel with thermodynamic properties. It is a physical manifestation of quantum correlations, and its entropy is a measure of the information required to describe that profound connection. This ties the arrow of time directly to the weaving and unraveling of the universe's quantum geometric fabric, suggesting that the reason time moves forward might be deeply connected to how entanglement and these hidden space-time connections evolve. But in every journey of exploration, we inevitably arrive at the ultimate question of origins. Where did our entire cosmos come from? The standard Big Bang model points to an initial singularity, a state of infinite density and temperature from which space and time themselves erupted. Yet the concept of a true singularity is a sign that our physics breaks down, a placeholder for our ignorance. What if the birth of our universe wasn't a singular, inexplicable event, but was instead a connection, a bridge from something else? This leads us to a breathtaking theory where the very genesis of everything we know is a wormhole phenomenon. The idea flips the script on our cosmic story, proposing that our universe didn't simply appear, but was born from a connection to a far grander, pre-existing reality. At the heart of this radical cosmology is the concept of the white hole. We've already encountered white holes as the theoretical exit point of an Einstein-Rosen bridge, a region of space-time where nothing can enter but matter and energy can only pour out. They are the perfect time-reversed mirror of a black hole. Imagine now taking this concept and scaling it up to the absolute limit. What if the Big Bang itself was the white hole end of a primordial wormhole of unimaginable scale? In this scenario, the incomprehensible fireball that marked the beginning of our universe wasn't a point of infinite density contained within our own space-time. It was a gateway. Our entire cosmos began as the mouth of a wormhole, connected through a vast cosmic umbilical cord to a parent universe. The tremendous outpouring of energy and matter that we call the Big Bang was simply the contents of that other universe flowing through this bridge into a new domain, inflating and cooling to become the expanding cosmos we inhabit today. Our universe, in this view, isn't a closed, independent system. It is a branch, a budding offspring of a much older and larger cosmic structure. This concept finds a powerful and elegant extension in physicist Lee Smollen's theory of cosmic natural selection or fecund universes. Smollen proposed a truly Darwinian mechanism for the cosmos, where universes reproduce and evolve. The process begins with black holes. According to this theory, when a star collapses to form a black hole in our universe, the intense gravitational collapse at its core doesn't just form a singularity that dead ends. Instead, it pinches off and forms a new wormhole bridge to a brand new baby universe. The interior of every black hole becomes the Big Bang of a new cosmos. This provides a stunningly beautiful mechanism for cosmic reproduction. Universes give birth to other universes through the formation of black holes. A universe that is proficient at making stars and black holes becomes highly fertile, producing a large number of offspring universes. This is where the theory offers a potential solution to one of the most profound mysteries in science, the fine-tuning of the universe for life. The fundamental constants of nature, the strength of gravity, the mass of an electron, the force that binds atomic nuclei, seem precariously balanced. If any of them were even slightly different, stars would not burn, complex atoms would not form, and life as we know it would be impossible. Why is our universe so hospitable? Smollen's theory provides a compelling, if speculative, answer. Each new baby universe does not inherit an exact copy of its parent's physical laws. There is a slight random mutation in the fundamental constants during the birthing process. Most of these mutations would produce sterile universes, realms where black holes cannot form. perhaps because stars never ignite or because the forces are too weak to cause gravitational collapse. These sterile universes would have very few or no offspring, but occasionally a mutation will occur that makes a universe even better at forming black holes than its parent. That universe would then produce more offspring which inherit its fruitful physical parameters. Over countless generations, a form of cosmic natural selection would favor those physical constants that maximize the production of black holes. And here is the crucial, elegant connection. The very same conditions that make a universe proficient at creating black holes, the right balance of forces to form stable, long-lived stars that can later collapse, are also the conditions that are necessary for the formation of heavy elements and the emergence of life. We find ourselves in a universe fine-tuned for life, not because of divine purpose or incredible luck, but because we are the product of a multiversal evolutionary process that selects for universes that are, by their very nature, fecund and fruitful. Visualizing this cosmic genesis story requires the most epic of imagery. Picture a vast, ancient parent universe, its galaxies swirling in a darkness punctuated by the brilliant death throes of massive stars. As one such star collapses, its core does not simply vanish into a point. Instead, the fabric of space-time twists into a brilliant, funnel-shaped vortex, a wormhole bridge. On the other side of that bridge, in a realm that did not exist a moment before, a new reality blossoms into being in a fireball of incalculable energy. This is not an explosion into a pre-existing void, but the very creation of space and time themselves, unfolding from the mouth of the wormhole like a flower from a seed. Our entire cosmic history, from the first flash of the Big Bang to the formation of galaxies and planets, is the story of that one budding universe growing and maturing, itself now filled with stars that will collapse into black holes, each one potentially holding the seed of a future cosmos within its heart. This transforms the cold, impersonal vacuum of space into a vibrant, evolving ecosystem on the grandest possible scale, where every black hole is not a tomb but a womb. But perhaps the most pervasive and powerful source of this cosmic repulsion is already saturating the vacuum around us, dictating the ultimate fate of everything. This brings us to a theory that connects the grandest cosmic destiny to the most incredible engineering possibility, proposing that the fuel for wormholes isn't something we need to invent, but is the dominant energy in the universe itself. We're talking about phantom energy, a particularly ferocious and speculative form of dark energy. You'll recall that dark energy is the mysterious force causing the universe's expansion to accelerate, but phantom energy takes this to a terrifying extreme. Its defining characteristic is an equation of state where the pressure is not just negative, but is more negative than that of a simple cosmological constant. In practical terms, this means its repulsive gravitational effect isn't constant. It actually grows stronger over time. If phantom energy is the true driver of cosmic acceleration, then the universe is headed for a catastrophic end known as the Big Rip. In this scenario, the repulsive force becomes infinite. It wouldn't just push galaxies apart. It would first tear galaxy clusters apart, then rip stars from their galaxies, then tear planets from their stars, and finally, in the last fraction of a second, it would shred atoms, nucleons, and the very fabric of space-time itself. It is the most violent conceivable end for the cosmos. Yet, within this apocalyptic force lies the seed of a staggering technological dream. The same property that makes phantom energy so destructive on a universal scale, its intensely negative pressure, is precisely the property required to tear open and stabilize a wormhole. Think of the fabric of space-time as a sturdy, elastic sheet. Creating a wormhole requires you to puncture this sheet and then forcefully push the edges of the puncture outward, fighting against the natural tendency of the fabric to snap back together. Normal matter and energy simply weigh the fabric down, making the puncture collapse even faster. But phantom energy is different. Its gravitational repulsion is so potent it acts like a cosmic crowbar. In theory, if you could concentrate or manipulate phantom energy in a localized region, you could use it to forcefully pry open a hole in space-time. The energy wouldn't just prevent the hole from closing. It would actively push the boundaries of the tunnel outward, holding the throat of the wormhole in a permanently inflated state against the immense gravitational pressure trying to crush it. The phantom energy itself becomes the perfect, self-sustaining lining for the tunnel, providing a constant outward push that requires no further intervention. The engineering vision for such a feat is as grand as the cosmology behind it. An unimaginably advanced civilization wouldn't need to manufacture exotic matter. They would need to become masters of cosmic hydrology, learning to channel the flow of phantom energy that permeates all of space. They might develop a kind of gravitational dam or a set of focused fields that could gather and concentrate this diffuse energy into a specific, targeted locus. Once a sufficient density was achieved, the repulsive force would become so intense that it would literally blow a hole in the space-time continuum, creating the nascent mouths of a wormhole. The engineers would then guide and shape this explosive event, using further fields to sculpt the erupting geometry into a stable tunnel, with the ever-present phantom energy flow ensuring the throat remains propped open indefinitely. It would be like harnessing a hurricane to power a city, but on a scale that manipulates the foundation of reality itself. This creates a profound and almost philosophical link between the ultimate fate of the universe and the pinnacle of space-time engineering. If our universe is indeed phantom energy dominated and destined for a big rip, then it contains, woven into its fundamental laws, the very mechanism needed to create stable wormholes. The force that will one day tear apart every atom is the same force that could, in principle, be tamed to weave the galaxy together with shortcuts. This suggests a civilization's longevity might be tied directly to its understanding of this cosmic force. To avoid being annihilated in the final big rip, a sufficiently advanced society might learn to use the phantom energy not for travel but for salvation. They could theoretically use a network of these wormholes to create isolated, stable pockets of space-time cosmic arcs, shielding themselves from the infinite expansion and repulsion tearing the rest of the universe apart. In this breathtaking scenario, the technology of wormholes becomes more than a tool for exploration. It becomes the ultimate lifeboat, allowing intelligence to survive the end of everything. For all these dazzling theories about wormholes, one practical and urgent question remains. If they are out there, how would we ever actually find one? We can't simply send a probe to investigate every gravitational anomaly. We need a cosmic treasure map, a set of telltale signs that would allow our telescopes to distinguish a wormhole from a star, a black hole, or a cloud of dark matter. Fortunately, the same physics that describes these tunnels also predicts unique observational fingerprints, giving astronomers a specific set of clues to hunt for in the vast darkness of space. The most promising and direct method relies on a phenomenon we already use to study the universe: gravitational lensing. We know from Einstein that massive objects warp the fabric of space-time, bending the path of light that passes near them. This is like a cosmic magnifying glass, and we use it to detect everything from planets around distant stars to the distribution of dark matter. A black hole, for instance, creates a distinctive lensing effect, often visualized as a perfect, bright ring of light known as an Einstein ring surrounding a dark shadow, the black hole's event horizon. A wormhole, however, would create a signature that is subtly but crucially different, because it is a tunnel with two mouths, and because the space-time geometry around its throat is unlike that of a singular, dense object. The lensing pattern would be far more complex. Instead of a single dark shadow, a wormhole might create two distinct, bright images of a background star or galaxy, separated by a peculiar central dim region. Or, depending on our viewing angle, we might see a broken or double Einstein ring, a set of concentric, luminous circles with a strange, empty gap in the middle, a signature that says tunnel rather than dead end. Beyond this silent warping of light, we might also detect a wormhole by the chaotic death cries of matter being drawn toward it. Imagine a wormhole situated within a cloud of interstellar gas or pulling material from a companion star. As this matter spirals inward toward the throat, it would be compressed and heated to millions of degrees, just like matter falling toward a black hole. This would produce powerful X-rays and gamma rays that our space telescopes could detect. However, the energy signature might reveal the wormhole's true nature. For a black hole, the high-energy radiation has a clear cutoff at the event horizon. Beyond that point, all light and information vanishes. But for a traversable wormhole with no event horizon, the story could be different. We might detect unusual flickering or a specific energy spectrum in the radiation that suggests material isn't just vanishing, but is being funneled through a narrow throat and perhaps even re-emerging elsewhere. It would be as if we were seeing the glow from the entrance of a cosmic tunnel, with a faint, correlated echo of light potentially detectable from its distant exit, a ghostly connection across the void. Perhaps the most elegant and unexpected detection method involves watching for the subtle twinkling of distant suns. This technique, known as microlensing, relies on the fact that even an invisible object will briefly magnify the light of a background star as it passes directly in front of it from our point of view. Our telescopes have used this to find countless rogue planets and brown dwarfs. A wormhole would produce its own unique version of this event, which we could call a star shimmer. As the wormhole's mouth moves across our line of sight to a distant star, its complex gravitational field would bend the starlight in a very specific time-varying pattern. The star wouldn't just smoothly brighten and then fade as it would with a simple spherical object like a planet. Instead, because of the wormhole's unique double-mouth geometry, we might witness the star's light flicker or pulse in a rapid, double-peaked pattern. It would brighten, then split into two distinct, superimposed images for a moment, and then merge and fade away. This rapid, complex dance of light, recorded in the precise photometric data from observatories, would be a powerful statistical signature, a ghostly footprint of an invisible tunnel drifting silently through the interstellar medium. To make this search a reality, astronomers are now training advanced machine learning algorithms on vast streams of astronomical data. They are creating millions of simulated observations, feeding computers with artificial data that shows what a wormhole lensing event would look like amidst the noise of variable stars, distant supernova, and instrumental glitches. These sophisticated programs are learning to pick out the unique gravitational signature of a wormhole from the petabytes of information collected by missions like the James Webb Space Telescope, the European Space Agency's Gaia Observatory, and the future Vera C. Rubin Observatory. They are searching for that broken Einstein ring in deep field images, that anomalous X-ray flicker from a quiet patch of sky, and that telltale double-peaked shimmer in the light curves of millions of monitored stars. The hunt is no longer a matter of mere speculation. It is a rigorous, data-driven forensic investigation of the cosmos, a patient scanning of the heavens for the subtle architectural flaws that reveal a hidden doorway. And so we arrive at the final, and perhaps most human of our 30 theories, a point where our journey through the physics of wormholes brings us face to face with their ultimate meaning for us. This isn't a question of equations or exotic matter, but of consequence. If these cosmic doorways were ever flung open, the impact would resonate far beyond our laboratories and starships, striking at the very core of who we are and what we might become. Imagine a future where the first stable wormhole is declared operational, its shimmering mouth a gateway to a star system rich with untouched worlds. In that single moment, the paradigm of human existence would undergo a shift more profound than the agricultural or industrial revolutions combined. We would transition almost overnight from a planet-bound species, anxiously guarding our single, fragile oasis, to a galactic civilization with access to the near-infinite resources of other solar systems. This is the dawn of a true post-scarcity society. The relentless competition for energy, rare minerals, and living space that has defined so much of human history could simply evaporate. With entire asteroids of platinum and mountains of gold available for the taking in other star systems, the very foundations of our economy would be rendered obsolete, forcing us to reimagine concepts like wealth, work, and value from the ground up. Yet, this utopian vision is shadowed by a chilling existential risk, one rooted in the fundamental laws of physics themselves. The process of creating or stabilizing a wormhole involves manipulating the fabric of space-time in ways we can barely comprehend, poking and prodding at the deepest architecture of reality. Theoretical physicists have long contemplated the idea that our universe's vacuum is not in its true, most stable state, but is instead a false vacuum, existing in a precarious, metastable energy valley. The immense energies and distortions involved in wormhole engineering could, in theory, act like a needle popping this fragile bubble. This event, known as vacuum decay, would be the ultimate and final catastrophe. A bubble of true vacuum would form at the site of the wormhole and expand at the speed of light in all directions, rewriting the very laws of physics as it goes. Atoms would disintegrate, forces would cease to function, and all structure in the universe would be erased in an instant. There would be no warning and no escape. The stakes of our cosmic ambition could not be higher. A single miscalculation wouldn't just mean the end of humanity, but the end of physics as we know it, a silent, perfect erasure of cosmic history. Beyond this ultimate physical danger lies a more immediate and complex web of ethical dilemmas. Suppose our first wormhole doesn't lead to an empty system, but to a world orbiting another star, a world that already teems with life. The moment of first contact would not be a slow, cautious approach from afar with robotic probes. It would be instantaneous and direct, an unannounced arrival on the very doorstep of another civilization. The potential for catastrophic misunderstanding is immense. Our mere biological presence could be a weapon, introducing alien microbes that act as a plague upon an ecosystem with no natural defenses, or we could fall victim to pathogens for which our immune systems are utterly unprepared. This is the problem of biological contamination, but on a scale that spans light years, compressed into a single step. The ethical frameworks we've developed for exploration on Earth, like non-interference and planetary protection, would become matters of interstellar survival, requiring a wisdom and restraint we have yet to fully demonstrate even among ourselves. And then, we must confront the profound psychological and philosophical shifts that would inevitably follow. For all of human history, distance has been a fundamental, tangible reality. The vast gulfs between stars have defined the scale of our cosmos and our isolation within it. But with a network of wormholes, the galaxy would shrink to the size of a neighborhood. The light year would become an obsolete unit of measurement, replaced by the transit time through a tunnel. This collapse of distance would fundamentally alter our perception of time as well. With the possibility of wormhole time machines, however unstable, the linear, one-way flow of time that has structured every human life and culture could become malleable. This would challenge our deepest notions of causality, responsibility, and identity. If you could potentially visit your own past, who are you? Are you a single, continuous self or a branching tree of possibilities? Our very sense of being, of having a unique and unrepeatable life story, could dissolve into a dizzying hall of mirrors. Ultimately, the discovery of wormholes would hold up a mirror to humanity, revealing both our boundless potential for growth and our immense capacity for error. It would present us with a choice far greater than any we have faced before: to remain a quiet, contained species on our pale blue dot, living in harmony with our world but forever confined to it, or to seize the terrifying power of a cosmic architect, risking self-annihilation for a chance to walk among the stars. The wormhole, therefore, is more than a scientific concept. It is the ultimate test. It asks if we are mature enough, not just technologically, but ethically and spiritually, to handle the keys to the universe itself. The answer to that question will determine not just our future, but the legacy of humanity in the cosmos. From the elegant simplicity of an Einstein-Rosen bridge to the terrifying grandeur of a cosmos birthing new universes through black holes, this journey across 30 theories has taken us from the very edge of a black hole's singularity to the shimmering, hidden dimensions that may underpin all of reality. We've seen how these cosmic shortcuts could be forged from the scars of the Big Bang, held open by the phantom energy dooming our universe, or even woven from the very fabric of quantum entanglement itself. Wormholes stand as a magnificent monument to the power of the human mind, a concept born from pure mathematics that has blossomed into a full-fledged field of scientific inquiry, challenging our most basic assumptions about distance, time, and the nature of existence. They are more than just a tool for travel. They are a key, a theoretical key that could unlock the doors to quantum gravity, resolve the deepest paradoxes of black holes, and reveal whether our universe is a solitary island or one bustling metropolis in an infinite multiverse. The true wonder lies not in any single answer, but in the sprawling, vibrant landscape of questions that these theories have opened up. Every time we think we have a handle on the concept, a new wrinkle emerges, a connection to dark energy, a potential link to consciousness, a way to sidestep exotic matter with modified gravity. This relentless refinement of ideas, this constant push against the boundaries of the known, is the very engine of science. It's a process driven by a fundamental human trait, an insatiable curiosity about what lies over the next horizon, or in this case, what lies on the other side of a space-time tunnel. The decades of work by physicists from Einstein and Wheeler to Thorne, Morris, and Maldacena demonstrate that the pursuit of a seemingly impossible dream can yield profound insights, forcing us to confront the universe on its own strange and magnificent terms, and in doing so, expanding our understanding of what is possible. So, as we reach the end of this particular expedition, the conversation is far from over. It's just beginning. We want to hear which of these 30 ideas captured your imagination most powerfully. Was it the haunting solution to the Fermi paradox, where wormholes explain the great silence by rendering entire civilizations invisible? Or perhaps the sheer, elegant power of the ER=EPR conjecture, tying the spookiness of quantum mechanics to the solid geometry of space-time itself? Maybe the terrifying beauty of a white hole Big Bang, suggesting our entire cosmos is the offspring of another universe, resonated with you on a deeper level. Let us know your thoughts and your own favorite theories in the comments below. This is a journey we take together, and your perspective is a vital part of the ongoing exploration. The path forward is lit by the twin beacons of theoretical innovation and technological advancement. As our gravitational wave observatories grow more sensitive, as our space telescopes peer deeper into the cosmic dawn, and as our quantum computers become more powerful, we are building the tools that could one day turn these mathematical speculations into observable facts. Whether we ultimately discover that wormholes are a fleeting feature of quantum foam, a dangerous impossibility guarded by chronology protection, or the hidden infrastructure of a galactic community, the search itself will undoubtedly revolutionize our place in the cosmos. If you've enjoyed this deep dive into one of physics' most thrilling mysteries, be sure to like this video, subscribe to the channel, and tap the notification bell. Our next adventure into the unknown is always just around the corner, and we'd love for you to join us as we continue to explore the wonders of the universe.